Okay, welcome to the first talk this morning. So it's my pleasure to introduce Denis Grebenkov. And so if we can put his talk up, I'll tell you what. This is a wonderful opportunity for me personally because I've never met Denis and I've only learned of things through his papers that he's written. So this is good. So his title is Search for a Small Target in Biological Cells, the Need to Go Beyond the Mean Rate.
Thank you very much, Michael, for introduction, and good morning, everybody. I'm a physicist at University Polytechnique in France. So first of all, I'd like to thank Michael and David for the opportunity to stay the next week in Pisa that I enjoy a lot. And today we'll present some results, relatively recent results. The title may sound to be far from the topic of the workshop, but in fact you will see that there are a lot of studies of PDE and also some asymptotic analysis. So as I'm a physicist, I will not go to present proofs, but I will rather present some ideas, and in some cases I will sketch the main steps of derivation, but then for details you can find them in the papers or we can discuss. And in particular, for some points, as usual, the level of rigor in the proofs is on the physical level. And so in some case I would be really interested to push it forward and to make it kind of on mathematical standards. So that's also one of my reasons to be here. So if you're interested in some points, I would be glad to discuss it with you, and maybe we can improve some things and do it rigorous as much as possible. Okay, I have also special thanks to Andrew, who yesterday made a fantastic introduction to all the topics, so I can go very fast on my introduction slides. Because so there are first passage and exit problems. They are very common in nature. On macroscopic scales, you can think of animals who search for food or for mates or for hiding. And on microscopic scale, it's the main transport mechanism for most of biochemical reactions, because some proteins or enzymes has to find specific locations in a cell or, for instance, on DNA chain to initiate some process. And so on mathematical terms, I will speak about just some Euclidean domain with the boundary. I will assume that the boundary is relatively smooth in this talk, so I'm not going to discuss technical issues related to very irregular boundaries. And on some part of the boundary, I will call it a target. So it can be a hole through which particle can escape, or it can be some catalytic site or molecule, whatever. And there is a particle which starts somewhere, and then it moves inside the domain, and then we would like to know what is the first time when it comes to the target. So formal mathematical definition is like that, so xt is our stochastic process. So the statistics of the first passage time depends on many things. It depends on the target size, shape, location, and type. It depends on the shape of the whole domain. It depends on the starting point position, and of course it depends on the type of the diffusive process. So in this talk I will focus only on just pure Brownian motion, well, reflected Brownian motion, because it is inside this domain, but I'm not going to discuss other possible extensions. So this is a random variable. It's characterized by a probability density function or cumulative distribution function. In physics, we more used to discuss survival probability. So it's essentially 1 minus cumulative density function. So it's a probability that the particle did not find target up to time t. And for normal diffusion, you know that's well-known mixed boundary value problem. So you have a diffusion equation, d is diffusivity, delta is the Laplace operator. Or if you want backward Kolmogorov equation with mixed boundary condition. So there is a Dirichlet boundary condition on the target. So if we start at the target, we are already at the target, so we cannot escape it. The survival probability is 0. And on the rest of the boundary, you have a Neumann boundary condition. So the probability flux is equal to 0. So particle cannot escape, and so it's reflected back and continues moving until it finds the target. The outline of my talk is the following. So I will present two different works. The first one is related to the mean first passage times in planar domains. And of course, this problem has been studied for a lot. And what I will argue is that, in fact, you can refine some asymptotics, and in particular, you can relate the mean first passage time not to the size of the target, but to the harmonic measure of the target. And in the second part of my talk, I will move to the distribution of the first passage times and discuss how you can obtain it and what are the properties, in particular in some kind of simple cases of geometries with separable variables. Okay, so let me start with the first part. We are interested in the mean first passage time. So again, what you need to do, so it's expectation of this random variable, given that we started at x0. And, well, just by definition, it's the integral of t to the probability density function, which can be related to the cumulative density function as a derivative, and here it has sign minus because it's survival probability. And so if you insert this relation into the formula for the survival probability, you immediately come to this Poisson equation with the -1 here and the same boundary condition. So again, everything was already introduced by Andrew, so I'm not going into detail. And in some cases, if you don't know where the starting point is, it's common to average over the starting point and to take something sometimes called global mean first passage time when you average over the starting point with uniform distribution. Well, in my talk, I will only focus on this more detailed information when the starting point is fixed, but of course afterwards you can make further analysis by integration. Okay, so this is an old topic, and I think maybe the first results, at least the first result I know, goes back to Lord Rayleigh, who looked on the escape from a sphere through a small circular hole of radius a, and he showed that it's proportional to the volume of the sphere, inversely proportional to the diffusion coefficient and to the radius. And then certainly there were other works, but I think kind of significant revival to this topic was done by David and his colleagues in a series of papers. And in particular, they provided the exact solution of the problem in the case of the disk, and when the target is just an arc of the disk. And this is one of the very few exact explicit solutions known to this problem, which is valid not only asymptotically for small epsilon, but for any value of epsilon. And in fact, well, if you write the mean first passage time in polar coordinates, radius and angle, then you can search a solution in this form, which definitely satisfies this Poisson equation, and then you have to fix the coefficients, unknown coefficients a0, a, and an. And then you have two boundary conditions that you have to satisfy that gives you two dual series relations. You can represent them in terms of the integral equations, so you can invert these integral equations, and finally you get the results. And the results look as follows. So this is the expressions for the coefficients. Well, again, this is the exact and explicit solution, but still you can see that the formulas doesn't look so pretty. Somehow it involves two integrals, but it's still what you can have. And in fact, if you work a little bit further on these coefficients, you can simplify them to much simpler expressions. And in that case, the formula becomes much somehow easier for numerical computations if you're not only interested in small epsilon. Because if you're interested in small epsilon, then you can make the asymptotic analysis that David and his colleagues did, and then you get the results. Okay, so then there are, of course, the asymptotic behavior which worked out quite accurately. So you have this leading logarithmic divergence, then you have a constant term, and then a term of order epsilon. It was also done for manifolds, so again you have this leading term, and there are other works, in particular in 3 dimensions for a sphere, but I'm not going to discuss them here, because in the first part of my talk I only focus on planar domain. So I would say, what is the current state of this field in 2 dimensions, at least how I see it, that you have in a narrow escape limit, you have a small parameter, which is essentially the relative perimeter of the target. So it's perimeter of the target divided by perimeter of the domain. And in the limit of when epsilon is small, the mean first passage time is proportional to the surface area, and it diverges as a log of 1 over epsilon. And so what I would like to convince you that this paradigm is not complete, and in fact it can be improved. And that you will see how it works. So why it's not complete? Well, let me give you two counterexamples. I insist that I put them in quotes, and you will see why. So first, let me consider very elongated rectangle, and I would like to know what the first passage mean first passage time to the smaller edge of the rectangle. Well, you can see because of this choice, it's essentially one-dimensional problem which has a very simple and explicit and exact solution. And you see that this solution, in fact, it doesn't depend on the height, so it doesn't depend on this parameter epsilon, which is formally introduced, so it doesn't depend on the relative perimeter of the target, which would be h over the whole perimeter. And even when h goes to 0, epsilon goes to 0, the mean first passage time remains constant. So in that sense, if epsilon goes to 0, it doesn't mean that t should diverge. Well, in this particular example, it can still remain relatively small. And the other example is the following. Take again a disk. Take one small arc and replace this arc by a very long curve. You can even take a fractal curve if you like. And in that case, again, what you can see, you can make this relative length of the target as close to 1 as you like. And if you take the fractal curve with infinite perimeter, it would be exactly equal to 1, right? But still, even by intuition, you would expect that the first passage time would not be 0 in this case, right? Because it has to go to find this place. So in that sense, and when epsilon is large, well, by large I mean that close to 1, it doesn't mean that t is of order 1. So it doesn't. Again, this relation is not satisfied. I say that this is a counterexample in the sense that, of course, as if you go accurately into this analysis, you can see that this asymptotic analysis that was mentioned yesterday in particular, it's applicable for what I would call regular domains, when the perimeter of the domain is somehow proportional to its diameter or to the square root of the surface area. And definitely these two cases are not in this situation. But still, it would be nice. These examples are quite artificial, but you can easily imagine more realistic situations in which the same features would appear. So it would be nice to get some description which would take into account these particular situations. Okay, so now this is the problem. So again, I reformulate the Poisson equation. Here I even allow diffusion coefficient to be space dependent. But it doesn't really matter, so if you don't like it, you can just forget about it. But the solution works even for space-dependent diffusion coefficient. And in fact, in this case, I will focus on simply connected planar domains, and also I will assume that the target is also simply connected. And then it's very natural suggestion, and in fact, I was quite surprised it was not done before. Well, and I hope it was not done before, because anyway, I didn't find any references, that you can just make conformal mapping to the disk. So in fact, there is a conformal map from the disk to this domain due to Riemann theorem, and this conformal map is determined up to 3 real numbers. And so 2 real numbers we fix by choosing that the starting point has a pre-image just in the center of the disk. And there is the last point which in fact would, the last parameter would determine the rotation of the disk. So I would impose that it is symmetric with respect to the horizontal line. So I can write it as an arc from minus pi omega to plus pi omega, so in this region. So in this way, the conformal mapping is fixed completely. And you can easily realize that in fact what is omega here is nothing else than the harmonic measure of the set gamma seen from the point x0. And the harmonic measure, again, Andrew mentioned it yesterday, it's the probability that the Brownian motion started from x0 hits the boundary on the subset x for the first time. And I would like to emphasize the difference between the harmonic measure and the mean first passage time problems, because with harmonic measure, all the boundary is absorbing. So on the whole boundary, you put Dirichlet boundary condition. On the other hand, for the mean first passage time, it's only Dirichlet condition here and Neumann on the rest part. But still, they will be related in quite interesting way. So once you do this conformal mapping, it's essentially just change of coordinates. So you can rewrite the original problem as a problem for the disk, and the price to pay is just the Jacobian which appears on the right hand side. And in fact, because Jacobian depends on the z point here, in fact, I can also introduce d which depends on x. It doesn't matter. If I manage to deal with Jacobian, then it's for no price, for free, I get this extra dependence. So in the rest, I can focus on this problem. It's still a difficult problem because you have still mixed boundary condition, but the geometry is much simpler. Okay, so now we can forget about mean first passage time. So essentially, we just need to solve this problem for some function f0 on the right-hand side. And we do it in a very standard way. So first, you decompose your solution in two parts. The first part here is a solution of the inhomogeneous equation, but with homogeneous boundary condition. So here's the Dirichlet boundary condition. Oops. Did I wrong? What did I wrong? Sorry. Okay, good. Thank you very much. Okay, and so this problem is extremely simple to solve because it essentially applies the green function in the disk, which is known explicitly. And so there is a second part of the solution, which is the solution of the homogeneous equation, but with mixed boundary condition. And in the boundary condition, now you account for to ensure that you have 0 here. You account for the solution of the first problem. And so for this homogeneous problem, you also split it in two parts. One which would be symmetric with respect to the reflection with respect to the horizontal line, and the other one is antisymmetric. So you can write it in this way, and again you have some f, which would be just a combination either symmetric or antisymmetric of the functions v from the first problem. And you will see why, because in fact now if you have a symmetric solution, then you can search for a solution in the same form as in David's solution for the disk, but with just for the disk itself. So you can decompose it into cosine functions and polynomial in radial part. And then this again, you have to satisfy these two boundary conditions, so you put them here. You get these dual series equations, and then you can use this technique provided by Snedden from the potential theory to represent the solution in an integral form and then to invert the integral transformation. And finally, you get this expression for A naught. And you can also get the expression for an. It's similar what I gave before for the disk. But actually we don't need it, because we say that our conformal map is such that the starting point is mapped to the origin. So we need only solution at the origin. And so all the terms here with an would vanish. And in the same reason, we also don't need to solve the problem with antisymmetric part, because that would involve sine functions and again radial parts, but they will start from 1. And so they all will vanish. So in this way, this was just a particular choice of the conformal mapping, which facilitates the computations a lot. We only need this coefficient A0. So now, if I take everything together, so I take expression for this function f, then expression for the function v, I made some simplifications on integrals. At the end, I get the following representation for the mean first passage time. So what you have here, it's some integral form. Here you have 1 over dx, and here you have some function which is explicit up to the conformal mapping. So if you look on this expression, you can immediately realize that this function is nothing else than the green function of the Laplace operator with mixed boundary condition. You take this right hand side, and then you just inverse the Laplacian, you get the green function, and that's what you get here. And in this green function, you can realize that the first part is just the Dirichlet green function. And if you take this integral, it would be the mean first passage time from the starting point x0 to the whole boundary. So if the whole boundary would be the target, if the whole boundary will have a Dirichlet boundary condition, you would just have this solution. But of course here we have some reflecting part, so when particle arrives onto the boundary it can be eventually reflected, and this is the second term which accounts for reflections. And the second term is this function w, which is fully explicit. Well, again, it may look not so nice, but it is fully explicit, and the only non-explicit part is this conformal mapping. And that's of course natural, because we aim to solve the problem for any planar, a simply connected planar domain, so it's just the appropriate change of coordinates we have to use. And, yes?
Here it's a factor 1 over 2 pi. Usually the leading order term is 1 over pi, so it means that there is a singularity in this conformal mapping in the second term. Sorry, let me repeat. Sorry.
Yes.
So let me repeat the question. 1 over 2 pi is when the singularity is inside the domain.
Mm-hmm.
When you have a singularity on the boundary, because of the image charge, you have 1 over pi. It means that in your W, you have a singular part also?
That's right. Just next slide, you will see it. Sure, you're right. And so just to say, well, you can say, well, this is exact, this is applicable to any planar domain, but it's still formal in some sense that, okay, you need then to compute the conformal map if you want to get the solution. But first of all, for the conformal map, there are many numerical algorithms to construct them, so it's quite relatively well-studied topic. And I think conceptually it's interesting that we can take into account this mixed boundary condition in somehow analytic way. So it's just an addition explicit term which appears here. And moreover, it's very convenient for us for getting the asymptotic properties. So just before going to asymptotic properties, well, these are just plots of this function. It's a very nice function defined on the disk. So here's the case when you have target which is very small. Here's the case where the target is relatively large. But you see that this function has nothing special. It vanishes on the target, but apart from that, it's very smooth and nice. So let's go to the asymptotic behavior. And essentially, the harmonic measure, it's a probability, so it's between 0 and 1. And if the target is relatively small and the starting point is sufficiently far, naturally the harmonic measure, so the probability to hit the target for the first time, would be small. So it's very natural small parameters. And in that case, you can expand this explicit function, so it was just here, you can expand it on small omega, and you get the following expansion. So in this expansion, the first term and this leading term, and that would be essentially divergent term when omega goes to 0, it has exactly the same form as before. So here epsilon, it was a relative perimeter, but here is the harmonic measure. So dh, it's just we count if diffusion coefficient is space dependent, then it would be just the harmonic mean of diffusion coefficients. But again, we can forget about it, and that would be the same d as here. So in this sense, we get exactly the same leading term. The only thing that we changed the small parameter. Then you have the constant order term, which is explicit, and you can write down explicitly all higher order terms, because again the function w, it's very simple, so you can go to any order you like. But in fact, in many cases, practical cases, harmonic measure can be extremely small, 10 to the power minus 10 easily in some examples. So in fact, you don't need to go to very high orders. So these two terms would give you very accurate results already. I will give you some examples. So I think it's interesting that well, at least from my point of view, the natural small parameter should be not this relative perimeter, but the harmonic measure. Of course, then you can say that if the domain is relatively smooth, then it's well known that this harmonic measure is absolutely continuous with respect to Lebesgue measure. So essentially it means that the harmonic measure of the target, if target is small, is essentially the perimeter of the target times the harmonic measure density. And so because it's a logarithm, you can just say that you can just put the logarithm of the harmonic measure density to the constant term. And then you recover the previous form with epsilon. In that sense, I wouldn't claim that it changed everything, but I think it's still an improvement. Because first, this harmonic measure density, so this extra factor which you get can be very high or very small. So the harmonic measure can be very different from the perimeter. And second, this notion is also applicable to irregular curves. For instance, again, if you have fractal, then the harmonic measure is not, well, the Lebesgue measure doesn't exist anymore, and the harmonic measure is not continuous, absolutely continuous with respect to the Hausdorff measure. So it's a different concept. And in this way, you can still use these terms. And here's the point where I'd like to impact from mathematicians, because so how to make all these statements rigorous in the case of fractal curves or very irregular curves, that's kind of beyond my expertise. But I'm not sure that it's doable, because the harmonic measure exists in essentially any planar domain, and then the only trick you have to work when the mean first passage time exists if the boundary is very rough. Okay, so let's go back to just two examples I mentioned. Again, the rectangle. Well, you can compute exactly the harmonic measure in the rectangle, and when it's relatively far from the target, so if it's really elongated object, then the harmonic measure decays exponentially. You put this exponential into the first leading term, and then you recover the first term here. So, well, of course, you do not get the second term, which accounts essentially for the presence of this boundary. But this term would be recovered if you use the whole integral or higher order terms. But at least you on the right scale. And the second example here for a disk, you can see that in fact, according to the Makarov theorem, it states that for a planar domain, the information dimension of the harmonic measure is equal to 1. So essentially, it means that the harmonic measure density is somehow scales with the diameter of this target. And so if you use this relation, then you recover what you would expect for the mean first passage time, that the true parameter would be the diameter of this arc and not the perimeter. And so again, you can generalize it. Okay, so let me just illustrate how it works in practice and what you can gain with this approach. So here I constructed this domain. I fix the starting point. I fix the length of the target epsilon, and that what I will do, I will move this target along the boundary. So what you can see here, some numbers, are the curvilinear coordinates along this boundary. So according to this conventional form, the result should not depend on the displacement, so you would expect constants. According to this leading term, you would expect that it would behave as the harmonic measure of this object seen from x0. And this is what you see. So the blue curve is the exact solution of this integral equation, well, it's of course obtained numerically. The red one is just this leading term. And you can see that in fact it follows pretty well the exact one, and you can also appreciate that the difference between them is more or less constant, and this is exactly the constant that we miss just when we take the first order term, the leading divergent term, and the conventional solution, it would be just a flat part here. Well, there are some fluctuations, but these are purely numerical things. You can neglect them. So, of course, you can say, well, in some cases it's different by factor 3, so it's not so important. But in some applications, first, you definitely can make examples where it orders by factor 10 or 100. It's not a problem. So you can see that in this way, at least you qualitatively gain more insight on what's going on. Okay, so now I switch to the second part of my talk, and now I would like to discuss what can we say about the whole distribution of the first passage times. Yes, sure.
So in this example, actually the small parameter here can be what is called the narrow passage, that we develop in dire straight, where actually, if the passage from the point x0, to this funnel is of the same size of epsilon, then what you're showing, it's clear. It has nothing to do with the classical escape time, because this is the difficulty to go through this. So in that simulation, the order of this funnel, of this passage, was of the order of epsilon.
Oh, well, it's good. I think yes. Well, I would say that this length, well, I have to check exactly the number, but I think it's of the order. I mean, maybe it was twice larger, twice smaller, but they're definitely on the same scale.
So that's the reason why it is so different than the classical mean first passage time here. Because with this, you have actually a singularity that you have to desingularize. I will show how to, I will. This is what we did
I
10 years
agree.
ago.
I agree.
That's the reason. So it doesn't fall into this classical narrow escape.
Yes and no. I agree in sense that it doesn't fall to this what again I call regular domains. So this is true. But on the other hand, well, I think from what is interesting here that you have a rather universal way to account for different classes. So you can somehow reunite different situation. In the conventional case that you consider classical one, as I said, they are of the same order, so you get exactly the same thing. But in other cases, you can get more accurate things. In particular, the harmonic measure was extremely well studied, and there is an approximation that with balls, that if you want to estimate the harmonic measure of the set, you try to create balls, maximum balls as possible, and you count how many balls you get. Or balls or disk, I mean. Oh, sorry. Oops. As many disks as you can, and in this way you estimate the harmonic measure. And I think exactly it goes to the idea of this funnel, that when the funnel is very narrow, then you need many small disks, and then the harmonic measure is increased, and then so it's a somehow unified way to capture the singularity in some sense, of course. You kind of go from one problem for the mean first passage time to another problem for estimating the harmonic measure, which is not trivial, I would say. But it's much, from what I know, it's much more well developed. And it's easier because, again, you have just Dirichlet boundary condition. So you have a lot of probabilistic techniques which done for that. But we can discuss, I agree with you. Okay, other questions? Okay, well, I will be glad to answer later. Okay, now I switch to a second part about the distribution. Again, let me summarize how I see the state of the art. So again, when we want to compute the distribution, we need to solve the diffusion equation. And then naturally it's partial differential equation, so if you want to solve it, you would try to get rid of variables somehow. And so the first thing you would do, you would apply the Laplace transform because it removes your time variable. So you simplify the problem. Well, there is, okay. You simplify the problem, and then you would transform the Laplace, the diffusion equation to the modified Helmholtz equation. So you still partial differential equation, but you have one variable less. Exactly the same boundary condition. And just you can easily notice that when you take this pi, so the parameter of the Laplace transform equal to 0, you go to the mean first passage time. So you get again this Poisson equation. And well, for me it was quite surprising that this problem has been studied extremely well. Well, again, it's not fully resolved, everyone knows here, but I think there are several hundreds of papers, and there are exact solutions in some cases. There are many asymptotic results, and some of them we heard yesterday. There are many extensions beyond Brownian motion. So well, there are two nice reviews on this topic, but definitely there are more results. On the other hand, for this problem, which for me again it's still elliptic problem, so honestly I do not understand what is the fundamental difficulty to deal with this problem. There are quite few results. That there are solutions, well, in some elementary cases as an interval or a sphere, but apart from that you have just few approximations, and to my knowledge there is only one non-trivial solution, and this solution is not easy to get. So this is a common set, but still you need this distribution in many cases. So what was our suggestion? So we cannot solve this problem exactly, even in simple problems, so we designed another approximation, and that's what I will present you. So it's so-called self-consistent approximation or constant flux approximation. In fact, as I already mentioned several times, the main difficulty here is the mixed boundary conditions, and so the idea is can we try get rid of these mixed boundary conditions, and in this way simplify the problem. And so the idea was proposed, well, the idea of the approximation was given by Schupp et al. In 81 to solve a completely different problem. And then with Gleb Eshani and later with Ralph Metzler, we adapted this technique to the first passage times in this way. So we have this mixed boundary condition. What we can do, let's try to replace the Dirichlet boundary condition here by some effective condition. Oops. Oh no. Okay, well, definitely switching to Mac was not was not efficient. Okay, so here you have this effective boundary condition. I think it will appear later. But so the idea is that you replace this condition by also by Neumann condition, but in homogeneous one. And so let me illustrate the idea. So in fact, suppose you solve the problem. So you have you have a flux of probability across the boundary. So here I make just zoom of this target part. So you would get some flux of particles. And again, as Andrew mentioned yesterday, this flux is not constant. And moreover, near the boundaries you would get some singularities, right? So it's not clear how to deal with the problem. What we do, it appears to be rather tough. We say that we just replace this non-trivial distribution and even singular distribution on the boundary just by constant. So we assume, let's consider that the flux is just constant. Originally, we thought of that as a way to do iterative computation. So we start constant and then we take a next term and next term and next term. But surprisingly, it works so well. And you will see again the result. So we stopped on the constant approximation. But it can be done for other cases. Okay, and then, so this is general, and then you can do essentially for any situation. But then to get some explicit formulas and to show how it works, so to compute, we selected some basic shapes, and in particular a shape like that. So let me show what we do. Well, okay. Well, I'm afraid the second part will be quite shorter, because when I moved from my PC to Mac, all equation disappeared. I will switch to my computer. I'm sorry for that. Well, what can I do? I'm sorry for this interruption, but just let me see. Can you switch off this? It's embarrassing. it worked perfectly last week. Can you switch off the video? Just to the screen? Can you just leave my screen and not the video? Okay, well, I apologize for the resolution. Last week it was perfect resolution with the same computer. Okay, so I go back. So this is the idea. So here we approximate. So we replace this boundary condition, digital boundary condition, by Neumann one, but in homogeneous with some unknown flags that we will determine. And so let me show how it works. So we have selected this geometry. So just to make it clear, it looks like that. So you have two cylinders, one inner cylinder inside, and on the cylinder, inner cylinder, we put some annulus target, and then there is the outer cylinder here, which would be reflective, and there are also two planes which would limit the domain. And this choice, well, can be a model for some bacterial cells which also have cylindrical shapes, and in that case the inner cylinder can be the central region which can contain some nucleotides. So in bacteria there is no nucleus, but there's still region where the nucleotides are concentrated. But it can also be some other models. For us it is just a convenient domain in which essentially, well, you can do separation of variables, and in this way you can proceed with this approximation. Again, for the approximation it doesn't, it can be applied to any domain, of course, but then to check and to get some explicit results we need this computation. So we need to solve this modified Helmholtz equation, and it doesn't depend on the angular coordinate, it only depends on the radius and height. We have this inhomogeneous Neumann boundary condition on the inner target, so it's 0 in this part, and it's some constant flux on this red part, and it has 0 flux at these directions and 0 flux at the outer boundary. So essentially, yeah.
Theta is a Heaviside or a step function?
Yes, it's a Heaviside function. So just 0 or 1. So just to represent here it's 0 and here it's 1. Sorry. So essentially we have a particle which is confined in this domain, and then it comes to the target somewhere. So, well, all the rest is purely technical problem. I'm afraid it can be even boring to some extent, because then it's how to solve the standard differential equations. So you search for the solution in this form. Well, here you have a prefactor we just needed to get some right units. Then we put, as usual, the solution of the inhomogeneous equation with homogeneous boundary condition, so with Dirichlet boundary condition on the whole part. And this solution can be written explicitly in terms of some modified Bessel function. You will see it here. Then we have solutions of homogeneous equation. So these would be just radial solutions which would satisfy from here the modified Bessel equation. Here we put the part which is theta is just a substitute for z, well, because it's cosine, it was easier to write it in this way, but it's essentially just a shortcut notation. So theta is essentially z. And of course, so this is the form of these radial functions which appears explicitly. So you have modified Bessel functions of the first and second kind. Finally, there are these unknown coefficients which we have to learn from the boundary conditions. So let's see that by construction this solution satisfies automatically the modified Helmholtz equation. By the choice of the cosine function here, we satisfy these lateral boundary conditions. By the combination of Bessel functions, we satisfy the boundary condition and outer part. So the only thing we have to do, we have to deal with this part of the equation. And again, this is quite standard. So you take this solution, you substitute it here, you get something like that. And then essentially what you do, you use the orthogonality of cosine functions. So you integrate without the cosine function, you get the relation like this. then you multiply by cosine k theta and integrate again, and all the terms will vanish except some, and so you get expressions for the coefficients an. So you can see that in this way you can satisfy, you can relate all the parameters, and in fact you can express everything in terms of the coefficient a0, or equivalently in terms of the unknown flux that was here. So essentially what we did, we started from the original boundary value problem, which we didn't know how to solve. We modified boundary conditions, so we started to look on modified problem, where we imposed some unknown flux, and then we provided the exact solution of this problem, well, for this particular geometry. So the only thing, well, but still it's not complete in sense that we don't know how to decide, how to choose this flux, or equivalently, how to choose these coefficients a0, because this relation says that they're equivalent. And so we need some extra condition. In fact, and that's here why it's called self-consistent, because the idea was the following. So our original problem is to put Dirichlet boundary condition on the whole target. Now what we do, we add some weaker condition where we say that on average the Dirichlet boundary condition is satisfied. So we take the integral of our solution over the target and we impose, this is our choice, that it's equal to 0. We can have a long discussion about is it good choice or not good choice. And in particular you can see that this is still, so it's the Laplace transform of the survival probability. So it's a priori it's a positive function, right? And so when we impose this condition, it means that either this function should be 0 on the whole target, and that would be fantastic, that it means that we solved the whole problem, but it's not the case. Or it means that this function gets some negative values near the target. And of course you'd say, well, it's not good. And it is like that. So it's not good in the sense that if you are very close to the target, this solution wouldn't work. Well, this approximation wouldn't be accurate, because in particular it would allow for some negative probabilities. But in fact, for many cases, if you are not very, very close to the target, you will see that the approximation works quite well. But again, this is the step where I would like to know your opinion. Are there other ways to deal with the problem, more intelligent ways to impose this condition? But it's open, so I will be glad to discuss. So anyway, once we fix this, then we have only one constant which we need to determine. So we do this analysis and, well, we get the expression. I do not write it explicitly. So let me summarize what we have. So we get this solution. So again, it's the exact solution of the modified problem. And here you have some coefficients which looks like that, and here there are other coefficients which looks like that. So the solution is not elementary. You see, it involves many special functions, different series. It's a difficult problem. So we want to solve essentially time-dependent first passage time problem. It's not easy, but at least it's explicit. And from this we can get all kinds of asymptotics. So, and once this is the survival probability, once you know this expression, of course, you can get the probability density function, because again, the probability density function is the derivative minus derivative of the survival probability, and so in the Laplace transform it gives you something like that. So you know everything you want. And as the last point, well, I'm not going into much detail, but also you can consider imperfect targets as well. So in all my talk I spoke that the target perfect, it means that once a particle arrives it is destroyed immediately, and it was the Dirichlet boundary condition. For many practical applications the particles are not perfect. It means that the particle can arrive and has to overcome some energetic barrier to react. And so if it doesn't manage to overcome it, then it will be reflected in continuous motion and come back and come back. So this can be counted via the reactivity kappa. And essentially it means in practice that you replace the Dirichlet boundary condition by the Robin boundary condition. And again, when kappa is infinity, so this term disappears and you go back to the perfect case. But when kappa is not infinity, then you have to deal with this one. And so this kind of solution is applicable exactly in the same way to this problem. It just, again, the closure relation, so the last relation, it would be not that we take the integral of this function, but we take the integral of this one. and it has just minor changes in the solution. So it is possible to do. And quite curiously, it becomes more and more accurate when kappa is smaller and smaller. It's not surprising, but it's still interesting. Okay, as I said, first we need to check, does it make sense? Because we solve a different problem. We didn't solve the original problem. So to check this, well, we just computed the Laplace transform of the probability density function by solving the original problem by finite element method, trying to do it quite accurately to fight with all these problems, as Andrew explained. And we compare it with our solution, and you can see these are two cases of height of the target. So in one case, you can see that the target is relatively small, so it's a relatively narrow escape problem, and the agreement is good. And what was more surprising is that it also works for targets which are not small, because it's supposed we suppose that it should work only in the narrow escape limit, but in fact it works quite well even in a non-narrow escape limit. So here's essentially 1/3 of the whole cylinder, but still the agreement is remarkably well. Okay, so from this exact solution you can get all kinds of asymptotic behavior. So in particular, you can look on small target height or small radius of the cylinder. You can look on the small pi limit, so it means long time behavior, and large pi, it means short times behavior. The only problem is that you have too many lengths. So in fact you have the radius of the outer cylinder, the height of the domain, the height of the target, the radius of the inner cylinder, and also the length which comes from the diffusion problem. And in fact, when you look on the limits, you have to suppose what are the relations between these lengths, because the limits are not the same. And so, well, in the paper we analyzed several limits, but definitely there are others which we didn't. And in particular, by the way, I would like to mention that in fact you can also look on the unbounded search, also Andrew presented. If you take R goes to infinity, in that case you'd have just without cylinder, so you'd have a diffusion outside just a smaller cylinder, or when L goes to infinity, so it will mean infinitely long cylinder, or both. So this is also possible, and also you get some non-trivial asymptotics. So just to give you two examples. Here I only focus on the mean first passage time. I come back to the first part. So I took the particular case when pi is equal to 0, and so it corresponds to mean first passage time. And for instance, when the height is the smallest parameter and the radius of the cylinder is also relatively small, so then we get the following asymptotics. So first of all, you can recognize, because this would be essentially a two-dimensional problem. Well, also it's in three-dimensional, but because of the symmetry, it's essentially a two-dimensional problem. So you can recognize this logarithmic behavior as 1 over epsilon. Well, here 1 is corrected by rho, but rho here it's kind of big as compared to epsilon. So this is a small parameter. But I think what is more important here, that if you include this partial reactivity, you get this extra term, which in fact gives you the leading behavior in epsilon. So it's 1 over kappa epsilon. So again, when kappa is infinity, this term does not exist. But when kappa is not infinite, this term would be the leading term. So essentially, the narrow escape problem would be not diffusion limited, but essentially barrier limited. So how it's difficult to cross the barrier. And this is a very general, it has nothing to do with this particular choice of the geometry. We did the same for a sphere, we did the same for other cases. So for instance, for a sphere, normally you would expect 1 over epsilon, that would be your conventional behavior, but then you would have 1 over kappa epsilon square. So again, you would have leading term given here. I think that is quite interesting in the sense that if you neglect completely, well, you come back to the classical case, but sometimes you have to include it. And in practice, kappa can be large, but then you have large or small, so you have to still account. So this term in many cases can be dominant with respect to this one. Kappa is a reactivity of the target. So essentially it's related to the probability to be to react on the target once you arrive. And so when kappa is infinite, it means the probability is 1, you react immediately. But when it's not infinite, that the probability is less than 1. And when kappa is 0, the probability is 0. So it's somehow, it's a transition in between. Okay, and here it's just the other limit. Just again, it looks very similar, but here, okay, rho and epsilon, they change their roles, and naturally they change their roles here. So you have the different here. Well, there's also factor we change, but okay, that doesn't matter much. So you have this, and again, you can get these terms. You can try to compute high order moments, high order corrections. Again, you have an explicit solution. That's the advantage. Okay, so let me give you some practical illustration. Of course, all this analysis was in the Laplace domain. Now we would like to go to the time domain. And for time domain, unfortunately, we have to do it numerically. So you can get asymptotic behavior at short times and long times, and that we did. But to get the whole distribution, the whole PDF, you need to do it numerically. At least we don't know how to do it otherwise. Well, this is a typical situation. So this is just one example with relatively large target. And so this is how it looks like. So here you can recognize this is an exponential decay at long times. This would be the mean first passage time. So this is the standard thing because it's bounded domain. So naturally always would finish with exponential 1. You have very steep decay here, which is again very standard because you have a fixed distance from the starting point. And you see here the most probable values of the maximum of the distribution. What is interesting is that there are 4 orders of magnitude difference in between. So essentially, if you only look on the mean first passage time, it's not necessarily give you the correct time scale of your problem. So, and for instance, if you think about some biological situation, when you start relatively close to the target, it's essentially, it's often most probable value which would be more important in this case. Now, if, yes?
In the middle, it looks like you have a power law.
In the middle, it is a power law, in fact.
Yes, can you get the exponent there? Because that it looks like it doesn't depend on the old details of your.
This is true. Well, I would say yes, we can, and essentially, you can think about this as follows. So because we are if we are close to the target, so it means that we do not see outer cylinder. And so it is as we diffuse outside the cylinder. And here it would be the exponent as Andrew showed. It's 1 over t square root of log of t, something like that. That, well, because still the range of times is not very broad, I didn't kind of speculate about that, but it works. So in that sense, it's what you would expect. And moreover, what is and now if I try to reduce the size of the target, so here it's 1, 0, 1. So the whole height was pi, so it's essentially 3. So that one 1/3. So that would be like 1 over 30. So you can see that essentially, naturally, the mean first passage time it goes in this direction because the target is smaller, so it's more difficult to find. But the most probable value remains more or less the same, and so the distribution becomes broader and broader. And here it's again even smaller one. And you can see that it's quite curious that here you start to see some region which appears it's almost uniform part of the distribution. And again, it's not, well, once you see it, it's not surprising because of course you can explain everything from the scales and from the eigenvalues of the problem, because essentially this part is determined by the smallest eigenvalue of the Laplace operator in this particular shape, and it's very close to it becomes closer and closer to 0, and so the characteristic scale is 1 over this eigenvalue, and this part is dominated by other eigenmodes, and so they do not change much when you change this property. So again, you can all explain this, but it was quite surprising, at least it's the first time to see that you can see this almost uniform behavior over several orders of magnitude. Okay, and you can do the same thing when you change kappa. So here we fix the size and we change kappa, and you get essentially the same property. So the distribution becomes broader and broader because smaller kappa, it means that it's less and less probable to react when you arrive to the target. And so the distribution, and here you can again see this uniform distribution over 3 orders of magnitude. Okay, so let me conclude. For this second part, so this is we get this accurate and a full explicit approximation for the distribution. Again, it's only in the Laplace domain. From this exact solution, you can get the detailed analysis of the short and long time asymptotics that I didn't show in detail, but again, you can look on all these regions accurately. And I think, well, it's for more practical points that it's very crucial role of this reactivity parameter. And in particular, you can see in the asymptotic expansion of the mean first passage time, this can be the dominant term to analyze. There is this emergence of this extended plateau over several orders of magnitude with a uniform sampling of first passage times. And the most probable first passage time can be orders of magnitude smaller than the mean first passage time. So again, I think it would be interesting to move from the analysis of the mean first passage time to the whole distributions. And there are multiple time scales which are relevant for this search process. And with this, I thank you for your attention. And here, well, again, the summary of the papers I mentioned. And they're all available on my webpage, so if you're interested. Thank you very much.
Okay, do you have any questions? Okay, listen.
Okay. Essentially, I have a question and a note, a remark. And my question is as follows. This trick with putting the flux constant, as all tricks with putting something constant, reminds me very much of using some variational principle. Is there something known about variational properties or extremal properties of the mean first passage time distribution?
I'm afraid that that's a question to the audience more than to me.
Maybe.
I don't know.
So much like that, whatever you do, the result will be nice when you have a proper variational principle. That it's almost a nice thing to think about.
Definitely, I think it's a very good point, but I'm afraid that I cannot say something scientific right now about that. But I would be glad to hear the opinion of others.
Yeah.
What would that bring to put it in variational forms? What do you have in mind?
First, I have in mind the following. First, you know what inequalities are there, which for me is a very important thing. And second, you are on the solid basis. You say whatever you do, it's at least not bad if you know the bounds. And in many cases, you can also know the optimal bounds. So you indeed know the errors you can do. Because whenever you want to do something like this, whenever you do something like this, I will show tomorrow in the very stupid case how the variational principles are used or can be used. It's a very typical assumption. Okay, we don't know what the distributions are, what the situation are. Let's put something constant throughout the system.
Then you have in mind something more general than this. Because
Yes.
in this case, basically you can do a lot of stuff. But in your case, it looks like you
No, I was simply asking whether anybody knows about the variational principles for the first passage time distribution. Because essentially it's a kind of variational principle for a PDE. In many cases there are no.
The mean first passage time is the reciprocal of lambda
The
1.
mean is okay, but the distribution, because he was speaking about the distribution. For mean, I know.
Well, in some sense, since it's a diffusion equation, so you can also try to it has a weak reformulation, so this is clear. But if you can get something from that, it's an interesting question.
Yes, and my second is a no, it's a joke. So, because I was talking in a bar with your co-author, namely with Gleb Pashanin, who was putting much emphasis to the fact that the most probable first passage time is much smaller than the mean. I didn't think about this until now, until I have seen the pictures, and then I thought about the following. Okay, let's look at the Kramer's theory, at the simplest one, with the exponential decay. The most probable first passage time is 0. It's infinitely much smaller than the mean, and it doesn't play any role. there.
Ah,
at least.
I see your point.
Yes.
I think it's a good remark, and I wouldn't consider it as a joke. But for instance, if you have an exponential case, and think again, this plateau region, it's nothing else than this exponential part. So essentially, if you have the spectral decomposition, you would have one mode which can survived, and it gives you this exponential constant part, and the others are small. So if you have just one of them, of course, nobody cares about this most probable and this part of the plateau. What is interesting here is that you may here you have another time scale, which is relevant time scale of this maximum, which in many cases can be, I believe, dominant, and in this case, the transition in between is much more interesting. But you're right that for exponential case, it's a good situation.
So I really like that result that the natural small parameter is the harmonic measure in these simply connected 2D domains. So seems like probably the same thing is true in 3D, that the natural small parameter is the harmonic measure, but there you don't have the same conformal mapping tools. But, I mean, have you thought about that? Is there any way to sort of make the same statement in 3D?
I thought about that a lot, and I also tried to torture some mathematicians about that. Well, clearly it's not possible just straightforward, like brute force, because certainly in 3 dimensions you don't have all these conformal mapping advantages. And also, if you try to somehow guess what should be the form, again, it doesn't work. So in particular, you, in 3D, you would expect 1 over epsilon. So if you try to put 1 of the harmonic measure, it doesn't make any sense. And also, if you try to play with some examples like elongated cylinder or parallelepiped, again, it doesn't help. So again, it's you still have. So I'm pretty sure that the same effect and the same limitations of the conventional description would be relevant in 3D, but I have no idea how to approach this problem. Again, if somebody knows, that would be really great.
So an answer and a few comments. So actually, this approach in 2D was introduced short after we did this narrow escape by Avner Friedman in math literature, not in the physics literature. He has, and I think it's even now in the narrow escape, a page on Wikipedia. I think they put this harmonic measure on the This is what they have done, I think in 2006, something like that, 2006, Avner Friedman and some of the students, they started on this. So, and then to come back on your question, when we worked on this conformal mapping in higher dimension, what is important here is to use symmetries. The symmetries are the keys, because with symmetries you can reduce, and you have the Laplacian that can depend on 2 variables. But then the Laplacian that has 2 variables, usually there is a drift. There's a drift term. Because, you know, Laplacian, there is ddr squared plus 1 over r ddr. And this is like a drift. And now you have to, it's like a perturbation of your Laplacian. The Laplacian is r squared and theta squared plus 1 over r ddr. And this is the drift term that you have to consider as a drift. And now you have to see what's the drift, in which direction compared to where the holes, or if you have 1 hole or holes, if there is some symmetry in the hole. And then you can actually apply some of these ideas of conformal mapping.
Is it published, David?
This was done 10 years ago.
And published, you mean in 3 dimensions?
Sure, this is published in the math literature.
Okay.
In SIAM or in multiscale modeling and simulations, in the math literature.
Okay.
At that time, I didn't have in mind to publish in the physics literature. Can you come back on 1 second on your result, the last result about the cylinder, where you mention the effect of kappa, which is indeed to increase from, in dimension 3, from 1 over epsilon to 1 over epsilon squared. Here, you don't have 1 over epsilon squared, it's 1 over epsilon, correct?
Because it's 2-dimensional problem.
It's 2-dimension.
But in 3-dimensional, you have, so here you have leading conventional term is logarithmic, but then you have 1 over epsilon.
But I thought this is like a plate, this is like a cylinder in 3 dimensions, no?
Well, it's cylinder in 3 dimensions, but effectively this problem, because your target is rotation invariant, it's effectively looks at 2 dimensional. But we did the same analysis for a sphere. And for the mean first passage time, and then we got, well, again, you recover this 1 over epsilon leading term, and then 1 over epsilon square with kappa.
I see. So
correction.
you know actually that even, I think this is, Michael reminded me yesterday, we looked at a similar question in dimension 3, when you have a flat cylinder.
Yes.
We did that for to model diffusion in a synaptic cleft. So we could indeed obtain in the limit of L, I mean L is the length, right?
Yes.
L small, it's like a 2D problem. L large becomes 3D, and indeed you can see here the effect of 2D log and 3D 1 over epsilon. And indeed, to go to the question that was asked, now the position where you start is very important, because if you start just underneath, it's going to be absorbed. The probability to be absorbed compared to hitting the boundary is very high. So this is short time then, short time asymptotics. Well, if you start, and this is very important actually in biological context, because when you have a vesicle that releases content, it doesn't release just underneath where there are receptors. We know that it affects drastically the probability. So here what my suggestion is, there is also an important role of the initial position. When you put absorbing boundary condition on the on the surface, the outer surface, because then you can ask the question: what's the probability to hit one compared to the other?
Yes.
And that would be interesting. I mean, we did something again 10 years ago in a different context, but that would be interesting to look at, especially because the time scale will become important. For the direct absorption compared to the absorption, and then also look at the splitting probability.
Definitely. Well, this is kind of ready to do. I mean, you just change, because if you have homogeneous digital conditions on the outer cylinder, it's essentially the change of the functions Jn that I showed before. Just sorry, it's almost finished. Sorry. Okay.
Yeah, no, I understand that it is. You have the technique to do that.
Yes, so it's straightforward, so we can do it very fast.
Sure.
So let's maybe discuss afterwards the true application, but certainly.
Okay, I'll take one more.
Okay, so there is also a version of the Riemann-Waving theorem for multi-connected domain. And you can map it to a disk with slots. So maybe you can also use this to get some estimate.
That would be very interesting. Also, well, in my mind, it would be what kind of on my list to do is to consider when you have many targets, but simply connected domain. Because here, I still think maybe it's possible to do something, but definitely when you have some holes in the domain, I think it should be doable. But I need some support from mathematicians, because here I start to be not very competent on what kind of conformal mapping we have and how to deal with them. So if you're willing, I would be glad.
Okay, if there's no more questions, why don't we thank Denis again for a wonderful talk. Okay, so we're very efficient, exactly 11 o'clock. This is very good. All right. So for the person who needs no introduction, I'd like to introduce David Holcman, fearless leader, and he will talk about asymptotics of narrow escape, extreme statistics, and electro-diffusion.
Okay, thank you, Michael. Again, thank you for helping me organizing this week, and thank you for all of you to be here. I just want to introduce briefly what was our philosophy for the last 20 years? Because I think there's the math, there's what we're producing, but what is the philosophy? What is driving us? And why we are doing this? So I was interested in biology, but as an undergrad, I could not see, I was fainting when I saw blood. So I decided to move on to theoretical sciences. And then learning mathematics, I was not satisfied by the applicability. And so I waited until PhD and after PhD. And then I was still very much interested in the life sciences, about the complexity and how this complexity should be addressed. So the life sciences for many years were experimental. The finding were through an experiment. Not like in physics, where the idea that thinking could lead to discovery. Like general relativity started with thinking. In quantum electrodynamics, where people discover particles, they were discovered by thinking. And again, there are many examples. So it's classical in the physical sciences that theoreticians have a fundamental role in the discovery. Now it's much less clear in the life sciences. So we postulated that maybe we could discover, like people discover through the microscope, by using theoretical approaches. And so the idea was first, of course, to look at questions where we started with the physics, because when you start with the physics, you can derive things through equations, and then you write models. And then with the models, due to the complexity, the mathematics is tough, it's difficult. How you, for example, why should you derive an equation? Because an equation ultimately, as we have seen with the previous talks, allows us to see what is the dependency with the parameters and see specifically when they are a singular parameter, where that leads to infinities. And it's very hard to deal with infinities through simulations. But simulation were also important. Designing simulation, and efficient simulation, is a very subtle and important part of the business. But then, not only the question coming from the biology are important, then how to connect? You need to look at data. Data are important. And the idea that theoreticians are good to fit data, I think, is now past. Everybody understood that there is more. And the idea is that we can not only look at data, but see features in data that are not trivial, that are coming from the model. Now, how do you implement this program? It took me like 20 years to build a group where people could deal with data, write models, write equations, do simulations, and in the end, what we are interested in is to solve a question in biology by developing all of these theoretical sciences. So this is what I have been motivated by for the past 20 years. I'm still motivated by this. And I think it's important, not only for what we are doing, but also for our community, to deliver a message that, yes, it's possible not only to extract features, but to make prediction that people then can go to the experimental part of it and discover things. And also to understand, because the biology is very complex. It's extremely complex. And to describe such a complexity, the language of mathematical physics, asymptotics, is actually very appropriate. It leads us to understand timescale, behavior in a very refined manner. Okay, now I'll start the talk. So there's going to be 3 parts, but before that I wanted to dedicate this series of lecture to the memory of Zev Schuss, who passed away 1 month ago. So I wrote an obituary of 15 pages to describe how Zev started as a chief orchestra conductor, a pianist, and there is on YouTube concert, Chopin recital, where you can see him play. But he was also part of this story about the Tehran children. And again, I'm not going to summarize this here. This is a story of the children during World War II that went all across the Soviet republics and arrived later on in Palestine, now Israel. And this is Schuss here. And so this obituary is about this and its role in apply mass and all of this development, including my own development. Okay, so we have heard today the motivation for the narrow escape problem. I would like to give more biological motivation before entering into the analysis. Diffusion in cellular microdomains such as dendrite, spine, which are microdomains of neuronal cell, and the search for a small target. So this is the molecular aspect. Search for a target in cells like immunology, bacteria, and the best simple example is fertility. One ovule located in the uterus, many players, millions of spermatozoa, and they have to find a target in a very restricted time. Afterward, that's it. And we know that the number of sperm is crucial. If you divide by 4, let's say from hundreds of millions, you still have 20 millions or more, we know that it doesn't work. And it's still unclear why. And it's a crucial, significant problem for our society because, as you know, in the past 50 years, there's a clear decline in the number of sperms. And finally, I want to discuss a little bit today about the extreme events. So in some arbitrary, complex, high-dimensional space, you can see events such as when a cell stops dividing is to reach a threshold for the length of the telomeres. Fast activation during transduction, so this has to do with extreme statistic, that is when the first particle or the first something among many copies of identically distributed variable hit the target. The first one that hit, not the mean. Okay, and we'll discuss here the travel. An example is the travel of protein along a network, which is the endoplasmic reticulum. So this is an example here of simulation that we did more than 15 years ago, where you look at a Brownian particle. There's a small hole here between the plates, and we're looking. This was a model of crowding. People cannot measure experimentally this narrow escape by releasing here diffusing particle and looking at the time it takes to go across the neck. And probably Claire will discuss what's the probability and the time scale for particle when they enter here through a small hole to hit a very crucial part underneath a vesicle to allow the vesicle to free neurotransmitters. So just to give you an example of motivation, so we looked at this cylindrical cylindrical synaptic cleft here, asking what's the probability when those guys, 3,000 molecules, are released to hit one of this target before escape. And indeed, you can decompose this in eigenvalue, expand, sum this splitting probability, and see how it depends on the Bessel functions and the different parameters of the model. What's the role of redundancy? If you calculate this quantity, what's the probability for one particle to hit one of those guys is 0.001. So neurotransmission should never work. It should not work unless you have many particles, the redundancy, which allows to make this probability of the order of 1. Because otherwise the particle escape without hitting the target. Why it is important here? Because you have, let's say, 3,000 particles. Again, you can see the discrepancy between many thousands of particles and the number of target site, which can be 1 to 50. Okay, plan of the talk. I want to summarize briefly after what we have heard today and yesterday. Summary of narrow escape asymptotic approach. Green's function match asymptotics. Go to dire straight, which is really the using conformal mapping to study and to remove singularity when you have a singularity hidden in a cusp. And then I want to go to asymptotics for extreme narrow escape. And then I hope I have time to spend at least half an hour on the asymptotic for the non-linear Poisson-Nernst-Planck equation, which is a model of electro-diffusion where we spend now a couple of years working on this. We are still missing a good model, and I want to explain what would be future directions that are important for us. And I will mention open question during the sessions. So, briefly, from the stochastic equation, you can write the Dynkin equation, the backward operator, so you have to solve usually a mixed boundary value problem. U equals 0, which is on the target, DUDN reflecting outside the absorbing part, or you can have here partial absorbing reflection, and you want to find U as a function of epsilon, and if possible, what's the dependency on X. Usually it's very hard to do this in general if you have a vector field. So I will mention some cases where the field push everything to the boundary, so you have a motion along the boundary. This is what we did 10 years ago for vesicle motion. So basically the methods we've heard them, using Green's method, Snedon's methods, it's really Collins' method summarized in the Snedon's book, and the match asymptotic method, which has been very well developed by Michael and the people around him. So, of course, the Poisson approximation, because if the initial point is very far from the source, clearly, most of the regime what we are going to be interested in is the long-time asymptotics. That is, if you start with Fokker-Planck equation, you expand in eigenfunction, it's not necessarily a self-adjoint operator. In the limit where the particle for sure will escape, you can show that the survival probability and the mean first passage time satisfy the classical Dynkin equation with the associated boundary condition. And for a time longer than the first eigenvalue, you have this representation, and the survival probability just decay with a single Poissonian exponential. And this has been the basis of many simulations when you start far away from the target. So to summarize, the mean first passage time, we have seen this many times now. F2, this small patch, is 1 over epsilon when you start far away, plus order 1 term that depend on the position. And Michael spent a lot of time computing what is this order 1 depending on the initial position. In dimension 3, you have this correction of 1 over a, which is the curvature. And again, Michael has spent a lot of time looking, when you have a ball, what is this explicit order 1 term, which is important for what he said yesterday about the distribution of patches, looking at minimization problem. So, and of course, then when you have many holes, either through the Green's function, you can see the coupling, you have a matrix, and this describes well the interaction that you can have, dimension 2 or dimension 3. Then we looked 10 years ago at a different type of problem when there was a singularity. And for this, we use what Denis has described, a conformal mapping, not only to map this into, so we will see a specific type domain, but it was also to remove the singularity, because the singularity should affect the mean first passage time. And it does. Instead of having in dimension 2 1 over log, you get 1 over epsilon, where epsilon here is the size, the distance between A and B, and R is the curvature radius of these two disks. If you are on a Riemannian surface, you can have more complex structure depending on how you're going to approach here, not necessarily at order 2 with like a disk, but with any power. And then you have this mean first passage time, which depend on the power. In dimension 3, again, when you just rotate this, so this is where you use symmetry, this was to answer your question, you can use this conformal mapping, and then you get 1 over a to the power 3/2, not 1/2. And we did, again, variant, this was 10-15 years ago, what happened when you have 2-parameter expansion. Not only you have this epsilon here where you have to go and hit here the boundary, but you can imagine that the radius R1 divided by R2 can be of the order 1. So you can vary with a very narrow domain here to a domain which is of order 1. And this led, as you can see, to asymptotics where you can have 1 over epsilon and log over 1 over beta, where beta is this ratio, showing that they can play a role here. And now again, and this was important at that time, if you put an obstacle, you really put an obstacle where the small hole is located, instead of having log of 1 over epsilon, you get 1 over epsilon, right? And finally, when you have here a sharp angle, you can see how this sharp angle contribute or change the mean first passage time. Instead of having 1 over pi here, you have 1 over alpha. So then, a couple of years ago, we were interested in shaped objects because proteins are not just like ball or point, they have a shape. And so we looked at the following question: how long it takes for a rod to hit a small hole? And this is much harder because you are, if it's in dimension 2, you're actually in dimension 3. And the topology is the product dr, this is the domain here of disk of radius r, multiplied by S1, because the disk has S1 rotation. And so you end up with a three-dimensional Fokker-Planck equation. But if you map this into a three-dimensional domain, you end up here with a very nice question in differential geometry, where the small hole here become a narrow strip. And the boundary here, you just take this condition so that the needle stays inside the domain, so it gives you a condition, and the boundary is this equal to r. So you have two sheets that are there, and so you're interested in the mean first passage time to this narrow strip, and this is much harder because the mean first passage time to a rectangle has not a trivial flux. The flux is not 1 divided by square root of something. It has a different singularity. We were able to do this numerically. It's 0.7 because of the corner. So full expansion, so some question that we are still interested in, full expansion of the narrow escape in n dimension with arbitrary curvature with respect to this. This is still something important. Develop a narrow escape theory for shaped objects. What happens if you have a shape? I mean, how important is the shape? And we know that it is clearly there in when you have a protein or molecule that have to find a target, and the shape is important. So can we find generic framework for this, like starting with a needle? What is a narrow escape to a square window? We have numerical evidences, not yet any asymptotic. So we tried there a lot of conformal mapping. They're fantastic mapping. I think we exhausted the classics on there, so we have to find something new. Narrow escape with jump processes when you have a random walk, and what's the role of this delta t? It's still unclear. No infinitesimal operator. So we looked at this question for looking at a model of sperm. Sperm just move by rays, and when they hit the wall, they can be reflected randomly. And so it was very hard. There is no clear operator to use and to replace the Laplacian with this. So it's still an interesting question to calculate what is the mean first passage time for such a type of motion to find a small target, especially if you think about the uterus is not a convex domain. It has this kind of non-convex shape. Okay, and narrow escape for the general stochastic process. So maybe I'm not going to go much into the detail of how you go, because this is not very classical. How do you solve this equation? You use the classical Green's function. You express using Green's identity u as a function of g, and when you plug in here u equals 0 at the boundary, you end up with what you call the Helmholtz equation that you have to solve. That is, find the flux such that this is equal to 0, and find this constant which gives you the mean first passage time. And this can be done using the explicit expression of the Green's function, at least the singular part. We know what it is in Rn. In half the plane, we know that there is a factor 2, which is important due to the image charges. And when you integrate and you get information about the flux, that is du dn at the boundary equals this, you get information, the regular part of the flux in dimension 2, as was mentioned yesterday. In dimension 3, there is the singularity that you have to take into account. And you end up with having two equations for the leading order term here, two equations for two unknown, C epsilon and the flux, And ultimately, you end up with this elementary approach that we developed. We first published in 2004 to have an idea of what was the leading order term. Now, just something I wanted to discuss briefly is the additive property of the mean first passage time, the time to go from here to here, the time to go to the red, plus the time to go from the red to this boundary. So this is the additive property of the mean first passage time. And we use this basically, so Denis mentioned the singular effect here of a narrow tube. This is the mean first passage time here is finite. So we were interested many years ago, what happened when we connect a domain here where you have a small hole to a tube. And the effect of connecting the tube is that a particle, when it arrives to the tube, it can return infinitely number of times to the head. And so instead of having in dimension 3 1 over a as the leading order term, where a or epsilon 1 over epsilon, here what you get is 1 over epsilon squared because of this. So this is just this connection that it is summarized here. I don't want to go into the detail of the calculation, but basically the time to go from here to here, the time to go from here to there, plus the time to go from here to there, knowing that when you're here, you can return. That's why you have here this was at that time new. Now it's classical. This was published 2011. L is the length. D omega is the surface here. So if d omega in dimension 3 is pi a squared, you have 1 over a squared, 1 over epsilon squared. And the way you connect is important. Either you connect smoothly or you connect with a discontinuity. One leads to 1 over a to some power 3/2, and the other is just 1 over a, depending how you connect. Okay, and this is summarized here. We did that in dimension 2, in dimension 3, because this was important to understand how a receptor moves on the surface of a spine and to look at the effect of curvature. So to summarize, you have, yes, 1 over a squared, which is a leading order term, but the 1 over a or the 1 over a to the power 3/2 can contribute to 30%, because when a is small, this still goes to infinity. So there is some contribution here.
This shape is 2D or 3D?
They were both. So this is 3D. So you take this and you rotate by symmetry, or this is 2D, like this. So now the notion of the vector field. If you have the simple way to look at this question, I mean, we found this question by the analysis of how a neuron is growing. A neuron is growing by bringing the membrane. And where the membrane is coming from vesicles. And vesicles are produced around here, the nucleus, and then they move and they are extruded along microtubules and reach here the surface. But then when you have a neurite, it's growing in one direction. So where, even if you have vesicles around here, that they will be pushed along the boundary, they have to reach this place to deliver the membrane. And then this will grow. And so we were interested at that time, what's the rate at which vesicles arrive to this place when they are pushed? So they can be moved here to the wrong direction. So they will move basically in a boundary layer between here the surface and the inside of the cell. And so this is an example of representation where you have most of your vesicle located around, and how long it takes to find here the small hole. And basically this is like doing the problem in dimension 2, although there is a boundary layer, but it's unimportant. This is like a dimension 2 a problem where you move, let's say, around a sphere. If the field is in the opposite direction, that is, if you have an attractor, it's like activation, what Igor mentioned previously about activation. And then here what you can solve is a problem of activation, but not you have to, the escape only occurs through a small part. And this has been solved in 2006 by Zinger and Schuss. And here, so you could see that basically what comes into the rate is not the volume, but it's the surface. And this multiplied by the length here of the leading order term, the length here of this absorbing window. So briefly, we wanted many years ago to look at this question of desingularization, so I want just in 2 slides describe the methods of conformal mapping to remove the singularity. So we said, how do we remove the singularity? We have D Laplacian U. Let's use the Mobius transformation. Why Mobius transformation, you will see. It was a miracle to find that. So that when you plug that into the equation, you have the classical conformal changes. But what the domain looks like using this transformation. This is the domain. The domain is a banana shape where here what would be somehow the boundary layer near the hole becomes the entire domain, while the domain here will become just part of this, a small portion of this domain. In this banana shape, what was fantastic is that we could approximate the partial differential equation with 2 dimensions with 1 dimension, neglecting here the thickness. And we could integrate, and this is how we found this mean first passage time, which was 1 over epsilon, and r is the radius of curvature.
That's because the whole boundary is made of circular arcs.
The whole boundary
Is made of circular arcs.
yeah, I mean, we have to decompose the boundary slowly. This arc here, this arc are represented here, these 2 arcs. AB is mapped in here, and this entire domain, the entire, is mapped here. So what this says, it's unimportant what happened in the domain. What is important is what happened in this arc, and the position where you start here becomes very important. If you start here, but if you start there, it's unimportant where you start. Okay. Now I would like to tell you what we have been motivated recently, which is not the escape time for the mean particle, but the escape time for the first out of n. So let me show you simulations. We have n particles, let's say 1000. They start at point I. You're interested in what is the trajectory, the typical trajectory, and the time it takes for this first particle to arrive to point F. So those are examples here in green of typical trajectories for when there is only 1 particle. But if you are interested in the fastest, obviously you are going to select by a principle of minimization a trajectory that will actually be very concentrated near the geodesic. I'm not going to discuss that here. We use the Wiener representation of path integral to try to derive here some kind of variational principle. It's like the large deviation, but the parameter here becomes n. When n is large, the number of particles is large, you have to select in the integral of the Laplace type n times the integral of the energy for the motion. And so you go to the minimization, because when n is large, you find the path that is the one that minimizes it. So this was a different variational approach compared to the classical large deviation. Here, the parameter is the number of particles. And you see when you have an obstacle, you can see that you go along the trajectory along the geodesic. And what we can find as n is increasing, you can see that the distribution of the arrival time and the distribution of the length is actually getting more concentrated toward the one of the geodesic. So what is the mean time for the fastest particle among n to arrive to a small window of size epsilon? So for this, now we have to use indeed the entire problem. We don't want to go to large asymptotics because obviously the short time asymptotics will be important, because the fastest was actually selecting fast time to arrive. So we need to look at the entire diffusion equation and look at the distribution of the probability to arrive at time t for the first particle, which is the flux when the n-1 particles are still in the domain. Can you find a solution for this, at least asymptotically? So in dimension 1, when you have a domain which is just minus infinity a, and you start at a point, a fixed point inside the domain, you look the solution using not the eigenvalue, but using the Ray method, which was developed more than 40, 50 years ago by Joe Keller. And now in dimension 1, you just plug this into the equation, you calculate this probability to power n, and you end up with a mean first passage time, which is 1 over a squared, 4 pi d log of n divided by square root of pi. And if you have an entire interval, you have a series because it bounces back and forth, especially if you have reflecting boundary condition. And again, you can see how this is modified. It's not very much modified compared to the case of minus infinity a. It's 1 over, what's the most important result here is the distance to the point where the position here to the absorbing boundary. That's it, the direct ray. And this is the example of the theory versus simulation for 5 and 500 ions, so that we were satisfied with this agreement. And then we said, what about in dimension 3 or in dimension 2? So for this, we use, as Denis explained, the Laplace in time. And you have to solve this mixed boundary value problem. So you introduce the associated Green's function. And by plugging this, the representation of the Green's function, for this representation of minus delta plus qp equals d Laplacian with this mixed boundary value problem, you can express, as in narrow escape, p as a function of the Green's function plus the flux. The flux is the same. And then you go back to the Laplace, with the Laplace inverse, to the survival probability. And you end up with an explicit formula which gives you in dimension 3 how it depends, how the mean first passage time depends on the distance to the absorbing boundary. A is the size of the small hole, and n is the number of particles. And again, this is simulation versus the theory.
So it goes.
I'm sorry?
I understand it should go, it should increase even, not decrease.
Log of n is decreasing.
It's decreasing with n, should be increasing.
No, as n is the number of particles, the time should decay. It should be faster.
There are more possibilities.
Because it's the minimum.
Yeah, okay. So basically we did the same in dimension 2. And again, you can, in dimension 2 it's a little bit more tricky because it involves the sum of Bessel functions. We took this representation from actually one of your paper, Michael, where it was done carefully. So we'd use this, and again, we plug that into this ray, and we had the rays, and the rays is telling you that the trajectory, when there is no obstacles, because when there's obstacle it's more difficult, but there is no obstacle between the initial point and the absorbing part, it goes along the ray, and the time, again, is 1 over log of n, a log of 1 over epsilon. The log of 1 over epsilon is reminiscent from what we knew, but what is interesting here is you have a combination of n and log of 1 over epsilon together. And this is again some simulation versus Brownian simulations when you start at a point p0, again at a certain distance from the source. When we break the symmetry, we saw that there are two geodesic, but there's a geodesic which is shorter than the other one, and we indeed found here that this summarized that actually what the typical trajectory comes from the shorter geodesic. The one that is shorter is where you will find most probable the trajectory that will escape. Okay. Now, yesterday, Mike.
I have a question.
Yeah, go ahead.
Very short before you start next time.
Wait.
What is the trajectory length? In the Brownian case, it's infinite.
Yeah.
So what is plotted?
Yeah, so what we did is we refine at delta t. At delta t, we looked at the length, and we saw that the length was actually converging when we sum it to the one of the geodesic. So this is what we found, that as n increases, the length was finite. And there was the number of points was actually, you don't have, it's not a Brownian walk. It's not as delta t goes to 0. We have a finite delta t.
Yes, yes.
And so this finite delta t, we plotted this.
Number of steps.
It's number of steps, and it converges, and then essentially it's a non-commutative limit to some extent.
That's true. Yeah, that's right.
As results published, these previous ones.
This has been accepted yesterday or 2 days ago. It's first of all, we sent it to PRL. They said no, it has nothing to do with PRL. We don't even want to send it for review. So I didn't fight. So we went to PLA. So it's going to appear in PLA, physics letter A. Okay. Why we develop all of this? It came from a question that Michael started to discuss. Discussed significantly yesterday. Is about active target. Time t equals 0, you release calcium. Calcium is moving by diffusion. It binds here to what is called ryanodine receptor. And when it is bound to ryanodine receptor, if there is calcium in this structure, which is called the endoplasmic reticulum, calcium is released. And to that day, it's very complicated to quantify this structure, what this structure is doing. Why cells need the endoplasmic reticulum? So we ask a simpler question is, what is the timescale of calcium when there is such a structure compared to the situation when the structure is absent? This was a work with my collaborator, Eddie Korkotian from the Weizmann Institute. So this is a description of the ryanodine. When ions arrives, after 2 ions, you have release, or there are Serker pumps. When ions arrive, they are just pumped in. Now the question is it important where these channels are located? How can you address this question? And you have drawings where people put them a bit everywhere, probably by random. So we started with experiment. I want to describe 2 minutes this experiment. Suppose at time t equals 0, you release many particles in the head. This experiment, you know that here you have the endoplasmic reticulum, here you have nothing. Look at the number of particles inside the head. It decays with the blue curve. And this, it decays with the blue curve. At the base here, you have this red curve. So obviously, when at time t equals 0 particles are injected, very quickly, after a few milliseconds, you have something here. If you have nothing, you have nothing. If you have no ER, this curve is flat. So there is nothing here. And this is to say that it is, it's asymmetric. When you do things in here, you don't find any, it's first of all, in the absence or with this endoplasmic reticulum, it's the same. So there's obviously an asymmetry depending on the direction and depending whether or not you have this structure. Why is that? Why do you have this? So when we did simulations, we knew from this calculation that the time it takes to go in average from here to here is hundreds of milliseconds. Now, hundreds of milliseconds is not 5 milliseconds. There was a discrepancy from a factor, whatever, from 5 to 100 something. It could not be just artifact or a numerical error. It's too big. The question where this was coming from. And we struggled with this question, I think, for 3 years, 4 years. Until we did simulations. Simple, naive simulation. You release particles. And now the question becomes what Michael started to emphasize yesterday. It's about diffusion with active target. And the question is, where are the target? Because there was no information. Here we are at the sub-diffraction limit. No information about the localization. So we decided to, according to what we thought, to place the receptors. Receptor ryanodine was located at the base, and this absorbing one was located at the front. And so when we put to zero this ryanodine receptor, we saw nothing. No, at this place when you inject particles at the star, no particle were arriving at the time scale of 5 milliseconds. But when we had this induced calcium release phenomena, we could see calcium appearing here. And now it was clear that the calcium that was appearing here was not the calcium that was moving by diffusion. It was the calcium that was released here. But what defined the time scale? What was the time scale defined by? Because you need a messenger to tell how to define the time scale. And this is why we looked at these extreme statistics. You need 1 or 2 ions to arrive first to one of these targets. They will open the receptor, and then you have an avalanche, calcium-induced calcium release. And that's defined the time scale for the process. Now, with this, we came to our biology, our experimentalist, and said, look, is this distribution known? He said, no, we never heard of it. So why don't you go and look experimentally if this is true? This would be our prediction. Otherwise, because we tried all the different combinations, it didn't work, except for this particular configuration. Well, they did the experiments, and they beautifully found this distribution. They didn't look for that in their data before because the question was not asked. And indeed, they found, for example, for ryanodine receptor, that it was massively located here underneath the spine, while the sarcopomp was mostly located here and a little bit inside, but not at the base. Now, this was very nice. This was very nice that they could see and check our prediction and found that it was correct. Now, I just added this slide yesterday for Michael. The same theory, the same, nothing happened. And so we didn't, again, they had this data, they didn't look at these properties that I'm going to describe now. We said that if we have such a property, if the residual calcium by diffusion should activate this ryanodine and create some kind of puff. And it should be random, and the time scale should be associated with the first passage time of the first one to find those targets. And so we said we should find some kind of random or oscillatory type spiking. So it's not exactly an oscillation, there is no period, but indeed, we looked at what happened underneath here, the spine. We checked that nothing happened in here because it's not a stimulation. And we could see indeed this kind of what we would call some kind of oscillation, which is the interpretation of which we give to these extreme statistics of binding to these channels. And we extracted here time constant, and this time constant is actually the one that we calculated separately. Partial conclusion. Extreme statistics explain fast calcium signaling from the spine head and the amplification process due to ryanodine. The transient time scale is controlled by the arrival of the first 2 fastest calcium ion to a ryanodine receptor. Extreme statistics is defined by the first ion to arrive at this time scale, which is very different from the classical diffusion theory, and the measurement. The measurement gave also a very long time scale if there is no calcium-induced calcium release. And the arrival time scale is governed by the number of initial calcium ions that are released.
Just a short question. Why do you need 2 calcium? Why do you need 2 calcium ions to arrive? Why not 1?
Because this is how the ryanodine receptor works. This is a property, an intrinsic property. Okay, now I would like to spend the rest of the talk about something I wish I could do. I don't know how to do it. We have some progress, and maybe if you are interested, I'll be happy to share. I mean, this is an industry that is probably needed, and it has to do with the understanding of electrophysiology ions motion and interactions at this scale, at the micron scale level. So again, I presented to you this dendritic spine. It has a shape. So let me back up 1 second. You know that in some neurons you can have hundreds of thousands of these structures. It is clear, so for example during pregnancy, that 1/3 of this disappears. And then they regrow. So don't worry, Claire, they will come back. A question is, we still do not understand how memory is encoded in the brain and how geometry like this participate. They participate. We know that, so the disappearance of this structure is associated with a loss of memory. So naively, how to address the question of geometry? Usually in geometry, everything is about description. In physiology, it's about the function. But can we reconciliate trying to find how geometry could participate to this function through the physics, the underlying physical process? And through the conversion of, suppose at time t equals 0, this neuron activate chemically that neuron by releasing neurotransmitter, they will open the channel and there is a current. So the question is the following. Let's formulate the question and let's see how we could address it, how we can try. What is the effect of this current on this structure, and in particular, can we understand the difference of potential between this point A and point B? Because ions or ionic channels do not feel the current, they feel voltage. They feel voltage. We know that during synaptic plasticity, you can change the current when there are protocol which say that when an animal learns something, the current is increased. But the geometry here can change. So if the geometry change and counterbalance I, whatever you are doing with I, you have to, if it is counterbalanced, it will have no effect. So what is the role of the geometry? It's not a wire, it has a shape. What is the role of this geometry? To influence the difference of potential between a point here in the spine versus a point here when you are already in the dendrite. Can we calculate this? So when we started to look at this many years ago, we said, all right, let's look at the different ion concentration. And if you sum here the positive ion and the negative one, it's not balanced. It's not balanced. So you could say, but then everything will blow up if there is more positive charge than negative charge. It cannot be. Well, it's true. There are negative charges carried by protein, but they are moving at much smaller speed than ions. Ions are shooting very fast in the cell. Hundreds of micrometers square per second compared to protein that are be more static. So it means that electroneutrality, which is an assumption in the calculation of the length, it's an assumption. The field is not too big, and it has to go to electroneutrality. Thus it decays exponentially near a membrane. But we cannot assume any more electroneutrality here, at least at some scale. So if we want to solve this question, we have to look at all species. No electroneutrality at steady state, so it's unclear what is the length scale of electro-diffusion. But it's much larger than the Debye length, which is usually, let's say, few nanometer, let's say less than 2 or 3 nanometers, 5 nanometer maximum. So how do you describe ions? This is a complicated business. If you start with the Langevin equation, acceleration, friction plus voltage equals the random noise, and now we have to figure out how to calculate V. Do we need to add water molecule? This is usually, of course we need, but this makes the business extremely hard from a simulation point of view, because water molecule can screen the ions. So we are in an electrolyte, and there was some success by the group of Ryzakov to start looking at this electro-diffusion to predict what happened inside the synaptic cleft. So it has been already worked out that in some cases electro-diffusion is important. I mean, experimentally, people have started to look at this, and they found some results. And so now I would like to, so we discuss in some reviews that there should be a failure of electro-diffusion that will affect the distribution and that will affect mean first passage time. Okay, so in general, if you go to the Smolokhovsky limit of the Langevin equation, you have the particle, each ion, which should be driven by the electric field, and the electric field should be due to the position of the whole particle, plus the boundary condition that you have on the material, on the boundary, and there's a lot of boundary, the external boundary, the boundary of internal materials. So it's a mess. So, again, I'm leaving open the question of how to add water molecule in a way that it can be computed, not just writing the equation and that's it, trying to do something out of it. For the moment, we haven't succeeded. And again, how to put in the slow motion of this moving negative protein. So, what we have done in the past 10 years, and this is what people have done for the past 50 years, including Zev Schuss when he was working with Bob Eisenberg from Chicago. It's to go to the Fokker-Planck, what's called Poisson-Nernst-Planck. You have the Fokker-Planck equation, and you disregard the joint probability of each ion. You look at the density, and you add here the vector field, which is the gradient of the potential, and the potential you have to solve separately the Laplace equation, and these two equations are coupled because the density here is the one that you obtain here. So with two species, positive, negative, you get Laplacian phi equal this difference, and the Fokker-Planck equation for these two species that you have to solve. And in general, it's impossible to do something, getting some estimates or looking at an expression for the voltage between 2 points. So we have to do some approximations. Wait, maybe you need a microphone.
What kind of boundary conditions would you put here?
It depends on what you want. So boundary conditions, if you are interested in the time to go from one point to another, and the dendrite is a big reservoir, you can put the concentration is constant, equals to the one of the reservoir. This is a boundary condition for the species, and there is a boundary condition for the field. For the field, you can have a continuity when you have a domain which is just the same, just you are interested in this arbitrary interface. This is an imaginary interface. If it's a real interface, then usually, for example, with the field, we put dphi(dn) equals 0. We added at some point the effect of the capacitance, but of the capacitance of the membrane, you can neglect this. It's unimportant. Okay, first example that we did. Suppose you put Q positive charge in a ball. What is the distribution of charges? And if you have a small hole, assuming that each time a particle arrives here, you reset a particle according to a uniform distribution, how long it takes for a particle to escape, and how the field is important. So first of all, let's calculate the field when you have steady state. So for this, you put 0 dt equals 0. You have the classical Boltzmann distribution, and the Boltzmann distribution rho, it's exponential something. You plug that into here, and you have classical equation that it is used in the curvature field of Riemannian geometry. People had the same type of equation, Laplacian phi equals exponential phi, and here you have this renormalization. Find the solution for phi and how it looks like in the ball. Everything is symmetric, so you use this radial symmetry, and you have this boundary condition, dphi(dr) equals 0 at the center, and due to the compatibility condition, you have to integrate. This is just Gauss compatibility condition. The total charge here is what you find at the external boundary. Dimension 1, and this is very important because this gives you the behavior, and there is a log singularity that can develop when the charge goes to infinity. First of all, the profile is like log of cosine. So when lambda is the number of charge, when lambda divided by 2, when lambda goes to infinity, this quantity goes to pi over 2. So cosine of pi over 2 is 0. A log of 0, it goes to infinity. So it develops a singularity as the number of charge goes to 0. It goes toward this behavior. It's the same in dimension, so dimension 1. Dimension 2, the same, you can see appearing here the singularity as lambda goes to infinity. So this is dimension 1, dimension 2. Dimension 3, we don't have a formula. We have an asymptotics, that should be further checked, I will show you, but we don't have a final formula. What we thought about how to analyze this equation was to use at the flame. And what they used at that time is a change of variables so that these equations, the Laplacian u equal minus exponential u, to change it into a dynamical system. And this is how Gelfand introduced his variable to look at, there was multiple solutions, but Gelfand was in this region and we are in that region. So we start here, we need to find out what's the position so that you go to converge to this critical point, and this will give you the condition to have a solution. But this cannot be used to study the singularity in dimension 3. You cannot use this. You had to go to this match asymptotics or to this asymptotic that we did. Doesn't give the result of the behavior. So in dimension 3, we found locally the expansion near the center of the sphere. And we found this ansatz, the log singularity when you reach the boundary of the sphere of radius 1, and you can see how good is the approximation here compared to the numerics. It should be very good. It has not been proved mathematically that this is correct. I mean, this is, but we have many evidences that it works. And now, if you are interested in the difference of potential between the center of the sphere and any point, because by symmetry you can take any point on the ball, u0 minus u1 goes like a log of epsilon. It's not like a classical capacitance where you have C multiplied by Q is V. It's log of the number of charges. And you can see how things behave dimension 1, dimension 2, dimension 3. So what did I do? Shall I press? Okay, so this was for the case of the ball. And now what we did is to add a small hole. So the distribution, which was exponential, said that most of the charges are going to be located near the boundary. It's not like with diffusion, they are not traveling everywhere. The charges will be concentrated along the boundary. All right, so I have to go, yes. Thank you. More. That's it, it's too far. That's it, fantastic. Let me go back a little bit. Yes, thank you. Okay, so this is the undimensionalized variable. So this is just to summarize what I just told you. It goes like log of n, and the log goes from the boundary to inside. So the boundary layer, the log function, is also the one that goes inside. The boundary layer extends inside the domain. Log is very small. It's not exponential, it's very small. Okay, and so what we did at that time, we said, all right, if you want to do simulation with this, it's extremely hard. So what we did is, if you have, for example, some negative charges, a population of 2 charges, but you have more positive than negative charges, then you can just use regular perturbation to see that what I just explained to you works. And you have just a perturbation that is u0, or u is just the solution I just showed you, plus a perturbation which depends on the ratio of the negative to the positive charges. And what you have to solve is basically, again, the same equation that I've showed to you. So the motivation for going to these extreme cases is non-electron neutrality. So if there is a steady state with non-electron neutrality, it's extreme. It's probably some science fiction, but it's to show how the charges are going to be distributed and their distributions inside this ball, with no other fancy shape. Now, what is the mean time to escape from a small hole for an ion located in the bulk at this quasi-equilibrium? So let's do these thinking experiments. You look at one ion. When the ions arrive to the small hole, to maintain the steady state, you assume that one appears located with this uniform distribution. So you don't deplete, and you maintain the vector field. This is what it means. So you have to solve this equation, Laplacian u plus the gradient equal -1 plus no flux boundary condition and absorption here. In the case where you have a large vector field, you can use this, we make this approximation that the field is large, because it goes to, you have this slope. And basically you can locally deform your domain, everything is smooth, so that you can see that this equation becomes an equation in Z plus the equation transversally. And by approximation, you can show that then the mean first passage time is really the mean first passage time as if everything was moving in 2D, because the field is pushing everything on the boundary. So we neglected the effect of this boundary layer, and we could reproduce this the same ideas as I just showed you of what we did in his paper with Saneva. And basically what is important is just the mean first passage time in dimension 2, which give you the time for this ion to escape. And then we can calculate the flux, which is the quantity of charge divided by this time. So the conclusion that the ball geometry define the voltage drop, and the current is defined by the small hole. Can I take 5 more minutes? Okay. And then the spine has a shape, and the shape was this cusp geometry. Now, can we extend the notion of nonlinear mapping to a nonlinear partial differential equation? So we have this conformal mapping. Can we do something to calculate the difference of potential between, let's say, the center here and the tip of the structure as a model? This is important because, people now have, just last year there was a paper where people are not making nanopipette, where the concentration of ions that they put on the surface is very important, and they can do this specific measurement. This is a new technology that is now moving forward. And now the question is that you can put charges everywhere, or charges just on the tip, on this cusp, or charges just on the tip. So there are 3 different cases. So let me just do one. This is what we have done. So we are in 3D by rotating this circle by the symmetry. So I will restrict not to 2D. The 3D paper is still moving into journal to journals. We have to solve this equation, minus sigma here everywhere. And so, for example, we have 2 cases. Either we put sigma on the tip or not. Now you do your transformal mapping. You map this from this domain to the banana shape with this Mobius transformation. So you have not only this conformal factor here, but you have an exponential. And also you have to be careful about how you map the boundary condition. It becomes a boundary condition that depends where you are on the disk. But what is fantastic here again is you go from 2D to 1D. And now we can use all the information because in 1D we know how to solve the equations. Okay, so this is to explain, I've already explained to you how you go from these steps to the banana shape. To the banana shape we reduce to 1D. All the domain is mapped to an angle C square root epsilon. Yeah, I think we're repeating ourselves. So now we just go from 2D to 1D. And now the question is, how do you solve this equation inside the domain? So Michael described the match asymptotic method. Basically what you are looking for is a solution near the absorbing boundary, a solution inside the bulk, and you match. You know, this is what has been done for the past whatever number of years, and you are satisfied if you have this uniform expansion. So remember here that the solution should blow up as the number of charge goes to infinity. So near the boundary, you will have a solution that can go to infinity. So if this was constant, we knew how to solve v second equal exponential minus v. It's an autonomous solution. You multiply by v prime, you integrate. That's it. The difficulty is this term here, which depends on theta. But if it blows up, this theta, this is not due to this term. It should be only due to this. So the method we developed was to freeze this term, and to consider a region where it is okay to freeze this, especially near the boundary, because this was going to blow up. While inside the banana shape, this carried the information about the geometry. So this is important, while this one is going to be less important. And it turned out that this was the idea. So you change variable, you are inside the domain. This becomes second order differential equation, and you can solve this inside. You can even freeze that one, and you just have to integrate twice this. That's it. Second part, you are inside the domain, or you are at the boundary. If a singularity appears, I don't care about this term, the solution should look like this. The one that will have this log singularity. And then the question is, of course, then later on to find what is B. What is this value that we have frozen? We have to look for it. And so basically this was the uniform solution. It was something that explained what happened inside the banana shape. A log of B which contains a singularity, and A was a constant to find when we will match with what happened inside the domain, to have a conservation of the charge. And so with this we could solve everything. I mean, it's the first paper that has been published. It's involved mathematically, but you can find a dependency with respect to the geometry, epsilon, the boundary of the domain, sigma, theta. Theta is the coordinate along this cusp. And this is the comparison simulation versus the theoretical result. And again, what was interesting, and now we could calculate what is the difference of potential between the point S here at inside touching the dendrite versus C, the center, and so here this difference is related to the geometry. And again, this is the comparison of the numerics that we did versus the asymptotics. And the asymptotics is interesting because it shows here the role of the radius of curvature here at this point, the role of sigma, the charges. So the conclusion that the geometry matters. The geometry matters through complicated structure. So basically this is where we are. I mean, I don't want to go into more. I have more, but I think that should be enough. I'm going to skip also the 1D with the narrow passage. I just want to show you that we did some simulations, and again, if you have curvature or very fast oscillating curvature, this is different times, different length scale, we could see a difference of potential between the point here of maximal and minimal curvature. Curvature in this framework can induce a difference of potential. Is it true? Is it? I mean, this is now what we are looking for. How this is important in the context of neuronal cells. This is reminiscent of what is called the of ribosomes. You know, there is a structure of the order of hundreds of nanometer that can have a difference of potential of 200 millivolt. Now, nobody understands this, and we think. And it has large curvature, I mean, very oscillating curvature. And we're still struggling to understand this and see how to apply this concept. Okay. We need a model for non-electron neutrality. It's not clear. This was just preliminary, basically, progress. I think we don't have yet a full model to understand how it works. We have a boundary layer that extends with the log deeply inside, which can affect voltage inside the cytoplasm. And not just, as people thought, with this, the bi-lengths, after a few nanometers, that's it. We think that it's not, and there are experimental evidence now that sodium flow in a spine differently than an inert dye. There was a paper last year going in that direction. So we have to, of course, to revisit the classical notion of resistance capacitance. Derivation of IV conservation law remains important, and the time-dependent asymptotics remains open. We've done something on this, but it's not clear. And on this, I mean, as I mentioned at the beginning, we're trying to bridge between data to asymptotics. So for this, I'm not alone. There is a team that I'm trying to maintain across the year through grant to help me there. This is all the students that are helping me all the time. And again, I dedicated all of this to Zev Schuss, with whom for 20 years we develop all of this theory of narrow escape. Thanks.
Okay, so have a few questions, maybe not too many because we're a little, and then we can save a few for later, so I'll take a few. John?
Give me them.
This is more of a biology question. You mentioned it was a ryanodine receptor that requires two particles to reach it first before it can. Would you say there's lots of examples like that, or other types of receptors where you need 2 or 3 or more?
Sure, there are many. There's a redundancy here that is needed, it seems to activate. Cerca also needs to, calmodulin, you need 2 calcium ions for the calmodulin to be activated. In many cases, it's very rare. Even, for example, glutamatergic receptor, there are 4 binding sites, and usually you start with 2 glutamate to bind for a channel to open. It seems to be important that to prevent, let's say, activation by one random guy, so you need at least 2, and the probability to have 2 is usually much less, I mean, of course, but it seems to be redundant and very frequent.
And real quick, presumably when you have one bound, that one can fall off sort of on a relevant time scale before the second one gets there?
Yeah, so we accounted for that. In here we neglected this. We said one arrives and it doesn't have time to fall off. Usually it's very hard to get this constant, so we neglected that.
Thanks. Okay, do we have any more?
The approach to this problem of the first escape where you have n particles. So the way that I would like to look at it is to take the domain n-fold and look for the Brownian motion in n-fold dimensional, independent, and then try to look at the the geometry of the hole, and in that case you can maybe use the measure of the n-fold dimensional and get the asymptotic limit maybe.
It's a good suggestion. The way we did it, we looked at the Wiener process. We had a step delta t. So we looked at discretization. We had n particle, the discretization with delta t. And then you can write the Wiener integral. And indeed, when you condition, you made some conditioning, indeed it's like getting the domain to the power n. Then, after that, it's very, Wiener representation is interesting. To go more, we stopped basically when we said that, when in the calculation we found that there was an exponential minus n, and then you have the integral of x dot square, which is the energy associated to Brownian motion. I think what we found from simulation is that the trajectories doesn't converge to the geodesic in a sense that, yes, geometrically it is, but it seems that on the trajectory, the velocity is not constant. See, when you minimize and you do the geodesic problem, usually you minimize the action, and the velocity is constant along geodesic. So I agree with you, there is more to see here. We don't know how to do it. It's a new type of what Igor started to ask about this variational. There is here a variational principle, which is not usual, but I don't know how to formulate it yet. Maybe if you're interested, I'll be happy to show you what we have done. But this is interesting.
Yeah, it is. Yeah. Okay, why don't we thank David again? So I'll talk a little bit later.
Okay. Try to.
The nonlinear one looks really interesting with the idea of an arbitrary boundary and then there's a blow up in the region. Yeah, so it's,
Yeah, that's why I wanted to present it to you.
maybe some but I want to this first particle and then triggering something works. No,
Yeah.
I think that's really interesting.
Sure.
It was that first drive that gets there.
That's right.
So that was.
That's something that you can.
But then I understand the mechanism of that. Right? So yes, there.
That's right. And it defines the time scale. And it took us 2 years to understand.
Thank you.
That's right. It's the mean of the first guy gives you the time scale. It took us because we didn't understand. We wanted to apply an error scale and it didn't do that.
All right. Okay. I'll give people 2 seconds here to.
When should I
What's
finish?
your title again? You have an hour. So wherever we start,
Okay.
you have an hour, maybe an hour 5.
Yeah, to be honest, I doubt if I'll take it
So
anyway.
wherever we
Which
start, you have an hour.
thank you.
But give it.
I'll send you.
Okay, we'll start in 2 minutes. Get some water if you want.
Okay.
So Chris was saying that you're going to use overheads. I'm afraid there's no overhead.
Yes, I know. I'm very disappointed with that.
With the glass.
But I've done the next best thing is it would be quite difficult to do it on that. Yeah. Right. Yeah. Oops.
Oh yeah. Okay.
One more. Sorry, what's the title?
Asymptotics of biological tissue growth. Elementary asymptotics. You're referring to the title of the conference, yeah.
There is, but it means something different. Okay. Yeah, we're okay.
Are the people outside?
Count us fingers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 10.
Just one.
Yeah.
We'll wait just for one. He has an hour from when we start. It's okay? Yes. Okay. Okay, so let's start. This is our last talk for this morning. So, welcome here an old friend, right? Professor John King of Nottingham, who will talk about asymptotics of biological growth models.
Thank you, Michael. And thanks very much. It's great to be here. So this will be slightly different from, I guess, the main theme of this conference. A general remark first. I did have some films of some simulations that I'm not going to show on a Mac. So I suspect I'm not going to use the whole time. So I do welcome interruptions, even if you weren't doing them as a matter of course. This is a slightly mongrel talk because it's stuff I'm sort of used to talking about, but it's a great pleasure to be able to try and organise it in a way suitable for an asymptotic audience. it splits sort of into three parts. I'm going to start by deriving from a significantly more complicated tissue growth model what I believe to be the simplest macroscale formulation that has interesting behavior. I would sell it slightly more strongly than that because some of its properties are those present in much more complicated models as well. So the statement is that it's one way of starting to get understand mechanisms better in the context of very complex PDE models in this kind of area. The second part of the talk will be applying further asymptotic reductions to the model, that minimal model I've derived, and then I go back to deriving a minimal model using different mechanics. So that, roughly speaking, is where we're headed. So that this is pretty much as complicated as it's going to get. I've listed on the left the variables, the unknowns, on the right the parameters, some of which depend on the unknowns. So to talk you through them, it's a two-phase model. I'm going to have living cells and dead cells and their volume fractions, so they add up to 1. Everything is one type or another, although there's going to be a moving boundary separating the region I'm actually going to solve in from the surroundings. It's what I tend to call a 1.5 phase rather than 2-phase model, because I'm going to take a single velocity field between the two phases, which says the drag coefficient is sufficient that they go at the same velocity. There will be a tissue pressure because there's going to be mechanics in this, and in particular cell division is going to drive a compressive pressure because making new cells requires extra volume by pushing neighboring cells away. I should emphasize this is all at the macroscale level. It's all going to be PDEs, not cell-based stuff. There's a nutrient concentration which will determine how fast cells divide or die. It's a free boundary problem, so that the domain on which I'm going to be solving will be a finite domain that's growing or shrinking. The normal velocity of that boundary will be q nu, and I'm also going to need the mean curvature of that boundary, which is kappa. Okay, so the right-hand side is the notation for the quantities that appear. So Kb for birth rate, which will be an increasing function of C. Kd is the death rate, which is a decreasing function of C. Yes. Do I mean that? Yes. So the less nutrient there is, the faster the stuff dies off. So together those contributions form this mass conservation equation for the living cells, right? So the usual kind of convective derivative thing you see in the continuity equation on the left, and then the net birth rate on the right. So when cells die, they create dead cell material, so that's the Kd term in the M equation. But in order to get growth saturation, as observed, I'm going to need degradation of the dead material. So there's a simple linear assumption on degradation there. Nutrients going to diffuse in, so diffusion is much faster than growth, so diffusion is quasi-steady, and that's this equation here, and the stuff's consumed by the living cells. I'm going to make a couple of comments on this line. The first is a very naive one, that of course you need the d inside the divergence in the spatially dependent case in order to conserve mass. So I've been slightly puzzled by one or two things that's been said so far with the d outside the Laplacian, but somebody will explain that to me at some point in the mean first passage time business. The other thing I'll comment on is most of the talk will be on the simplest possible constitutive assumption relating the velocity of the pressure field, namely Darcy flow, where mu is proportional to the tissue viscosity, the viscosity of the tissue material. So I'm taking the tissue to be a Newtonian fluid, as I say, the very simplest case, and it's flowing through a porous medium. So I need to comment on that. So I'm happy to do that if we're talking about tissue engineering, where the growth is in a porous scaffold. But this thing has a much longer history that is routinely still used for cancer growth for reasons I don't entirely understand. It's furthermore odd because one of the first people to do serious cancer growth modelling was Greenspan, who was a very good fluid mechanist, and he was the one who initiated the use of this Darcy flow as if it were growing in a porous medium. Okay, so there, the field equations. There's one final parameter that appears in the boundary data. So I'm going to take the surroundings to be well mixed and scale the nutrient level to be 1 on the boundary. So it might be supplied by blood supply or whatever. But again, I'm going in some sense for the minimal case. Pressure, I'm going to need a regularization at one point, so I'm going to use surface tension. The attempt to interpret that biologically usually is cell-cell adhesion, generating something akin to surface tension. And then finally, the kinematic condition says that the normal velocity of the edge of the tissue is moving with the local tissue velocity. So that's almost a tautology, but closes the system, the free boundary problem. So what am I going to do? I'm going to do asymptotics, and unsurprisingly, epsilon is my small parameter. So you can see it appears in quite a lot of places. So it's already written down in a distinguished limit form. So degradation is going to be slow. So quite a lot of dead material will accumulate. And consumption is going to be fast relative to diffusion. So there's an epsilon squared in the diffusion equation. The upshot of that, as we'll see on the next slide, is the asymptotic structure is one of a thin rim. So the dividing material is confined to a rim around the core of the tissue, and the stuff inside is not dividing. And that's why you need epsilon in both of those places. You need the epsilon in the first one for it to get big, and that one for the nutrient not to diffuse in very far. Surface tension ends up having to be scaled that way to get a distinguished limit. And finally, and quite importantly for the things I'm going to say, there's this reasonable assumption about viscosities that the living cell material is much more viscous than the dead cell stuff. So the stuff in the middle you can think of pretty much being just water. So that's going to be low viscosity. And then the surrounding coherent cell material is going to have much larger viscosity. So that's the full setup. And the first part of the talk is deriving the limit case of that model as epsilon goes to 0. Okay, so the structure is just two regions. The rim region I'll talk about briefly now and actually come back to it towards the end of the talk. So the schematic there indicates what's going on. There's this dead core in the middle surrounded by this much thinner rim. Right, the dominant balance in the variable rim is a travelling wave reduction of the full system. That's recorded in the box on the right, which I split into two because locally it's just 1D because the rim is thin. The scaling's recorded at the top, so the distance from the free boundary in the normal direction, nu, has some small scaling epsilon to get you this thin rim, and then the other scalings you need to get a sensible balance recorded there. So the travelling wave reduction of the system on the previous slide with those rescalings and discarding the negligible terms is this one-dimensional travelling wave. So the continuity equations are Galilean invariant. Since we're in Pisa, it's as well to be saying that. So Galileo has something to do with this, and that's the reason why introducing this quantity W works. So I translate the free boundary velocity q nu off the normal velocity of the tissue itself, v nu. And those two quantities only appear in this combination W, which is important for the subsequent analysis. So here's the travelling wave boundary value problem. C infinity and Q are constants you determine as part of the solution to that problem. And they're going to be key. Q will be C infinity doesn't actually matter. Q will be a key ingredient in what follows. There's the remaining mechanics, so one-dimensional Darcy flow. And then the rim, not much is going on, but because the core, because the rim is thin, the overall governing system is all to do with the core, which is much larger in volume. So here's the equations describing the core. There's a net volumetric source, lambda, because the dead cell stuff is degrading. So that appears in the mass continuity equation, which ends up being this form. We've still got Darcy flow. And because there's no living cells, there's no consumption of nutrient going on. So Laplacian of C is 0. Because of this business here, this thing is a constant. In the core, C is just C infinity. And that's not going to appear again. John, your degradation is small, so the mass is conserved. The core is all dead, and it's not decaying. In the core, it is decaying. In the rim, it's not. Right, so that's the decay term. And yeah, so if I go back, it's this bit here.
So there's
right.
Probably some like exponential dip in the center. You'll tell us.
Yeah. So I mean, incidentally, the biological, you have to have that term to predict what in vitro tissue growth looks like, because it does always saturate. the biological interpretation of this term is not quite clear. It might be stuff getting squeezed out. It might be stuff being consumed in cell division. People always do it. Okay, so that's the matched asymptotics, if you like. I think probably even on the next slide, there's a few comments on it, and then I'll go straight to this minimal model I've alluded to at the beginning. So a few remarks. The travelling wave reduction doesn't depend on the tangential coordinates or time at all. Right, that's a deduction, it's not an assumption. So you write down the thin rim equations and then observe there's no dependence on tangential direction except in the pressure field. And furthermore, you can infer from the ordinary differential equations for the travelling wave that n is uniform around the free boundary. And that'll be important in a minute because it means the surface tension is constant, whereas cell-cell adhesion would otherwise depend on the cell density. Okay, the mechanics I'll describe in slightly more detail towards the end of the talk. But just to say that at this point that this viscosity splits into a much larger value in the rim than in the core is important. If you integrate this Darcy thing from rim to core, you pick up various contributions. This is just saying in effect that the free boundary moves with the right velocity. But then there's two extra bits. The fact that the rim is much more viscous than the core means it's hard to push around. So you get a contribution proportional to the velocity of the free boundary. And then there's this extra pressure contribution. And then this just comes from the boundary data. So this extra pressure contribution you can think of as being to do with this compressive stress. Where cells are dividing, they've got to push against each other. And that's reflected in the value of P naught, which will either push the cells in towards the middle to fill up the fact stuff's being degraded, or outwards if the overall thing is still dividing. Anyway, the upshot of this calculation is these conditions at the bottom. So you lose the original kinematic condition. You've collapsed the rim onto a surface. So that would be the kinematic condition. The free surface moves with the velocity of the tissue. But now the tissue is only going to be captured by the core. So the matched asymptotics say you add to the kinematic condition this surface source of material. So that's one unconventional feature of this beyond a model that arises in physics that I'll comment on in a minute. The pressure boundary condition, that constant can be subtracted out. We've still got the cell adhesion, but we've got this new regularization, which again appears in physics where it's called kinetic undercooling, but has a completely different interpretation in this context. Okay, so now I switch notation. So this part of the talk is joint with Joe Isles and Vanessa Stiles of Sussex, which is where the numerics come from that I'll show in a minute. So this is their notations. I'm afraid I've stuck to it. So U is now a pressure, it's nothing to do with the velocity. This is just restating in rescaled form the minimal model that I ended up with on the previous couple of slides. So again, I'd talk you now through what the terms look like in terms of, if you like, in terms of physics, rather than from the biological derivation. So the field equation, the one at the top, corresponds to Ely-Shaw reverse squeeze film. So Ely-Shaw is viscous fluid between two parallel plates. If you pull the plates apart, the size of the fluid blob, of course, decreases because you're losing volume, because you're spreading it out over a larger thickness. And that's well known to be unstable. Like the thing develops fingers, inward pointing fingers. And the physical mechanism of that is to do with the viscosity difference. If there's a finger pointing into the thing, it's easier to pull stuff out when there's less viscous material inside it. So that's destabilizing. And then that's the field equation. Now, in the boundary conditions, there's various contributions. The surface tension one is completely familiar in Ely-Shaw problems where people very often use surface tension. Kinetic undercooling is derived now from this is part of the biological model from the start. This is derived from the asymptotics, the kinetic undercooling one, which has been studied to some degree in in Ely-Shaw, but now we've got both of them. So they're both stabilizing. They are both genuine regularizations. Then finally, and something you don't get in the typical physical applications of the model, is this surface source. So there's a competition between the surface source Q and the volume sink, the one on the right-hand side of the Poisson equation. So normally growth in Healy-Shaw is regarded as stabilizing. So you might think this stabilizes. The trouble is the bigger you let the thing grow, the more scope there is for this thing to generate instabilities. So I've written that as ambiguous, and actually in some sense it's much more destabilizing than stabilizing. So of course you start by doing the very simplest thing, which is writing down the exact one-dimensional solution of that system, which gives you the pressure profile is quadratic, and the growth is initially linear, but then ends up saturating. Okay, so tissue growth phenomenologically is often described as having three phases. So exponential for early phase, which I'm losing because I've already gone to a stage where there's a big core. But then the two final stages this does capture, so linear growth, then leveling off into saturation. Okay, if you're a mathematical biologist, the first thing you do is look for travelling waves, but we've already done travelling waves as part of the analysis. The next thing you might do is look at linear stability, which is straightforward in the usual way and leads to an unsurprising conclusion. So if you just, we stuck to 2D, if you look at circular solutions, if the regularizing parameters alpha and beta are big enough, the circle is stable. If that inequality is not satisfied, it's unstable, and I'll show numerics in a second. For most parameter regimes, the most unstable mode is the one with the symmetries of an ellipse. But as the thing grows, it can pass through different modes, being the most unstable ones. So in principle, you can see more exotic configurations. I'll come to that in a minute, probably. I'll flip back in a second. So that's numerics illustrating that point. Left-hand side is the initial data. The middle picture is what it grows to, and that's a steady state in the regime that linear stability predicts stability of a circle. And then the right-hand side is where it predicts instability. So that thing does have symmetries of an ellipse. In fact, you do get multiple tip splittings even with this very simple model, which relates to the thing I commented on at the beginning. Much more complicated models do those tip splitting kind of phenomena as well. Okay, right, the other thing you do is you're trained in, and we're now, as will be clear, I hope, in the phase of having got this minimal model doing various asymptotic reductions of it. If you're trained in industrial maths like I was, the thing you routinely do is look at the thin film limit. So you collapse it down further by doing the large aspect ratio limit. And this turns out to be an extremely dangerous thing to do in this context, though I suspect people would still try if they weren't concentrating. So I want to talk you to two things. One, what result you get when you do it, which is this evolution equation at the bottom, which I actually rather like. Unfortunately, it's got nothing to do with the behavior of the thing, as I'll come back to. But it does show some of the things, some of the features present in the model. Okay, so the next two limits, one rescales the minimal problem, so introduces an epsilon that's not the original epsilon. There's a misprint here. That right-hand side should be epsilon squared. So you do the usual thing. So the x and y scaling is very different. So the leading order problem is just u, y is naught. So u depends only on x and t, and then you need solvability to get how u naught does depend on x and t. So equivalently Fredholm alternative, or however you want to view it. So you turn the handle, and this is the equation you end up with. So there's various ingredients that are consoling, and I would actually like to know more about this equation. So this is the bit we've seen in the 1D case already, if you ignore all the regularization bits. So that should certainly be there. That's the term that comes from surface tension. So as at least some of you know, I know, is the standard thin film business for porous medium flow driven by surface tension. The other term is also one I've seen years ago, which is this pseudo-parabolic regularization, which is slightly worse understood, but that's what you get from kinetic undercooling. So that's what the thin film limit of this problem looks like. Both the spatial derivative terms act in the right direction. They both stabilize. So apparently all the instabilities have got lost. And that's because the things that are unstable are the short wavelength ones. So unless you do linear stability as well as the thin film limit, You have to do them together, otherwise the thin film thing you get can be very misleading. Okay, so the linear stability is also more straightforward in this case because it's long and thin. It's basically one-dimensional in any cross-section. So you just do the linear stability analysis of the one-dimensional problem, and you find you do pick up short wavelength instabilities in the unstable regimes, unsurprisingly. Okay, so that's sort of intended as a word of warning for thin film limits, but many communities wouldn't do them anyway. So I think the only other limit I now talk about is the one of interfacial dynamics, by which I mean the limit in which you reduce the system from a field equation with a free boundary to a system where you just have to capture the free boundary. You don't have to worry about the field equation. So the places you have to put the epsilon in this case are recorded here. So at leading order, you've got the Laplacian of u is 0, and the gradient of u is 0 on the boundary. So u is a function of time, and again you turn the handle and get the solvability condition. And the final formulation is recorded there in general dimension, and then in 2D where you can explicitly do the final integral. So again, this is related to, but has extra ingredients beyond what's in the literature. So these final two terms are non-local curvature flow. Which, Andy, have you done non-local curvature flow? Various people have. Okay, so that's a known model. That's a standard forcing for curvature flow. So that term and that term together is sometimes called force mean curvature flow, where you get a constant component as well as a curvature one. But here you've got this volumetric sink as well. Okay, so I suspect that one with all four of those terms has not been written down before. That's the 2D case. That's to show, although it's not actually doesn't quite correspond to the limit I did, that if you start off with a long thin thing, it doesn't stay long and thin. Again, you get something that looks like it's going towards tip splitting, but in this case doesn't. It's more stable than that, and I imagine that ultimately evolves to a circle. So that's Cho's numerics again. Okay, so a couple of other comments on that system. Something that's reflected in the interfacial dynamics formulation is this simple relationship between volume and area. So unsurprisingly, the net volumetric growth is driven by the surface torus and the volumetric sink, and that's the precise statement of how that looks. I've given it this slightly pompous follow-up comment. So that comment has nothing to do with the mechanism for the instabilities, but you might argue it's something to do with why cancer, for example, would want to develop fingering morphologies, because it gives access to more nutrient, which is reflected in the surface source against the volumetric sink. So a sphere grows in some sense as slowly as possible relative to other surface morphologies. And again, I guess arguably a difference between physics and biology is cancer cells could evolve to sit in these unstable regimes. Right, so the linear stability analysis implies there are multiple bifurcation points. You could do weakly nonlinear analysis. That's pretty much the only thing I haven't tried to do on this problem. I think an interesting problem in analysis would be to classify what those steady states are. They're probably unstable, so they're probably not important in applications, but I think there's an interesting question there. I'm about to show a couple of pictures of the numerics. As I say, there were some films which I'm not going to show, but I'm happy to show people subsequently, which show tip splitting and so forth. So there's only two of them here. So Joe did it both by a sharp interface method where you track how the free boundary is moving, and that's the top picture. The middle one is the diffuse interface one, so something analogous to phase field for people who know about those approaches. And the results, so you smooth out the diffuse interface by having rapid variation close to the free boundary. And that's the results of that are in the middle, and then the comparison is at the bottom. So the one place you can see is the final stage of development where there's a very small difference between the two. So the various phenomena occur here. One is tip splitting, which is not being shown here. The other is topological transitions, which, so these things do very soon after this time step collide and close off the bit in the middle. So it's not straightforward to track through those transitions with the front tracking thing. With diffuse interface it is, but you've got to be slightly careful because once you've closed off a bit of the surroundings, you want to change the boundary conditions around the closed off bit. So it's not just the standard thing where you crank the handle on some diffuse interface formulation. And the other thing is just to show Joe and Vanessa had done it in 3D as well. I suspect the code didn't run so far, so you end up with morphology like red blood cell kind of morphology, but the modelling content is completely different from that. Okay. So that's the first two parts of the talk. When did I start? I'm going to underrun. That's probably fine. So as I commented right at the beginning, it's always been a slight mystery to me why people use Darcy flow as the default assumption for cancer growth, and I'm much happier using Stokes flow for it instead. So free growth rather than growth in a porous medium. So I'm now going to retrace my steps to the beginning of the talk and derive the minimal model associated with Stokes flow rather than Darcy flow, and also talk you through a bit more of the analysis of the rim that we did earlier. Okay, so what are the corresponding Stokes flow equations? So slow viscous flow, the inertia terms are negligible, so the continuity equations, the divergence of stress tensor is 0, which is the first one appears. Again, in the interest of doing the simplest possible formulation, I'm going to take Newtonian flow, Newtonian liquid as the assumption for the tissue constitutive properties on the time scales of growth. The only thing beyond standard Newtonian, incompressible Newtonian flow, this material is incompressible, but you're making more of it by cell division. So you get the final term in the second equation is the usual shear viscosity, and then there is the bulk viscosity term as well, which is the 2/3 bit, which I've defined so that P is the trace of the stress tensor, minus 3 times the trace, minus a third times the trace of the stress tensor. So there isn't an independent bulk viscosity, but you do want to add the extra bit to account for cell division. The free boundary conditions, I should have said they're on the boundary, so exactly analogous to before, the surface stresses are going to be entirely associated with cell-cell adhesion, namely surface tension, and the distinguished limit again now sticks an epsilon in that equation. The overall mass conservation equation is the next line down. So otherwise the equations at the top are almost standard Stokes flow. This is the main difference. So you're making or losing new material. That's the cell birth rate. So incidentally, you think of this system as water getting in very easily, so you don't have to worry about what's happening to the volume of water. So you can make new volume. That's what that term is. And then the same degradation term in the core we had before. So that was already true, but emphasizes the fact it's not standard incompressible Stokes flow. So I've rewritten it at this point in possibly a more conventional form. So that's the Stokes equations, and this is the non-standard div V equation. Okay, so because the boundary layer, the rim analysis in terms of the transport is entirely independent of mechanics, I wanted at this point to step back and revisit it. This doesn't add very much to what we had before, but I start at the top with just a reminder of the equations we're using for both Darcy and Stokes in terms of N, M, and C. There's the rim scaling, the epsilon again, the thin rim, and here's the Galilean invariant business that defines W nu, the normal velocity of the tissue relative to the normal velocity of the free boundary. So here's the travelling wave reduction. I'm revisiting this because it underpins both systems, so I am largely repeating myself, I think. So here's the three ordinary differential equations that in effect determine what's going on. Here are the boundary conditions we've already seen. Here are the far field conditions that say C goes to a constant and W nu goes to a constant, but you have to determine them as part of the solution. So this one-dimensional problem determines is crucial in determining what free boundary conditions apply, whatever the constitutive assumption, because this is entirely independent of mechanics. So there's various deductions from that, which I've already alluded to, not made explicit before. That is the formulation. So you in general, you start off writing these as partial derivatives. That's all the asymptotic, leading order asymptotics would say. But having written them as partial derivatives, you then stare at what the boundary value problem is and realize they're not actually partial derivatives. The solution to this thing will only depend on zeta. It's a correctly specified boundary value problem for these variables. Okay, so each of those quantities depends only on the normal direction away from the free surface. A consequence of that is these things are constants rather than being dependent on time or tangential variables. And a further deduction from this system to do with this business and the fact that W is naught on the boundary, you find on the boundary you get a simple algebraic equation for n, which tells you that n is uniform and therefore the surface tension coefficient is uniform. Okay, so continuing now with the thin rim analysis, and the point I now want to emphasize is that the mechanics works in a completely different way from the two constitutive assumptions. So this does in slightly more carefully how the Darcy flow calculation goes and where this extra pressure P naught and the kinetic undercooling Q nu come from. And again, this is repetitive if you followed everything I said earlier. But now I'm explicitly separating out the two viscosities at the top. So mu naught you think of as the tissue viscosity and mu1 as the dead gunk viscosity. Without loss of generality, you can write it in the form I've written it, because if there's no tissue, the mu naught term is absent. So you then expand in the rim in powers of epsilon, and you have to go to two orders, because this one determines the modified kinematic condition here, but the first one determines the regularization and the extra pressure. So that right-hand side, again, you know everything about the zeta dependence from the W. The Q is just a constant. So this is the form the solution takes as an explicit integral over the rim of the first term there, where this is the solution to the boundary value problem. Q nu is simply a constant. We deduce that, so you can pull that out the front. Sorry, it's not a constant. Q nu is the viscosity, is the velocity of the free boundary, right? So that doesn't depend on zeta, but does depend on everything else. But you can pull that out of the front of the second integral. And the reason I'm trying to hammer that point home is it explains where the kinetic undercooling regularization comes from. Matching sends zeta off to minus infinity, so this thing is a constant, that thing is a constant, but this is pulled out the front. And again, that's to do with the fact that the less viscous stuff has trouble pushing the more viscous stuff around. And there's various other equivalent statements about that regularization. So matching to the core, we need information from both of them. From the second equation, we don't need to integrate it. We just note that everything goes to zero except two parts of it where I've now dropped the suffix naught. So that constructs the kinematic condition we've seen. But then the leading order switch in the pressure constructs this extra pressure contribution from cell division and the kinetic undercooling regularization. Okay. And because P1 is growing like zeta, the kind of undergraduate argument that P0 and P1 become at the same order, so the inner expansion breaks down, occurs when zeta is order 1 over epsilon, which corresponds precisely to the core. Okay, so now the genuinely new bit as far as this talk is concerned, and that's the mechanics for Stokes flow around the edge. If anybody's tried to derive viscous shell theory, it's a pain in the neck. This is like, because you have to go to 3 orders. Because of cell division, this is viscous shell theory, but with cell division it's slightly easier because you only have to go to 2 orders for reasons I haven't fully understood. So Peter Howell's thesis has derivation of standard viscous shell theory, which is where I nicked most of these equations from, but other people have done related stuff. So you have to do a tiny bit of differential geometry. So I write the free surface in terms of 2 tangential coordinates, Tor1 and Tor2, which I take to be like to parameterize lines of curvature. And then these A terms are the moduli of the tangential derivatives recorded there. The stress tensor components end up being expanded in this form. So the dominant parts of the diagonal bits just involve the pressure and various bits of the net growth and velocity. Again, Galilean invariance is coming in, so there's just W's. And the minus 4/3 there cancels the fact there are two of the ones at the top. The normal components of the shear stress, in other words, the shear stress on the free surface, are also order 1. Come back to these, and then there's bits which are just order epsilon, which you do need to worry about computing to get the solvability conditions that close the final system. So at leading order, the momentum equations with using the differential geometry kind of business end up being these. So these components end up just being identically 0. So remember, I scale surface tension with epsilon, so that doesn't appear in sigma nu. So with those results, you can read off how the pressure has to be, and then in turn you can read off how the other diagonal components of the stress are. And finally, you can also read off the variation of the tangential velocities across the rim. So as promised, you also need to go to order epsilon. There was slightly sloppy transcription in the first equation. So there's two equations for the tangential components of the stress, and they're the two at the top. But the final term should involve the other I than the remaining terms. So there is cross-coupling between the two tangential components. But fortunately, their leading order contributions are the same, so it didn't matter that I put I's on the final term instead of J's. And then the normal velocity one is the one below. And there you can see the seed of what's coming, that the two principal curvatures, kappa 1 and kappa 2, are multiplying diagonal components of the stress tensor there. That's the general statement of what the momentum equation looks like at order epsilon in this thin rim limit. You go through the relevant contributions and you find the correction terms to the shear stresses are also 0. But then most importantly of all, you have to compute the correction terms to the normal stress. So there's the bit I've imposed as the free boundary condition of surface tension, but then there's this extra contribution which is driven by the fact the volume expansion has said these sigma tors are non-zero, and they're driven by the birth rate. So that's the integral, the final integral in that middle line. And then again, match from rim to core, I have to take zeta off to minus infinity. So that integral becomes a constant. Again, the thing inside the integral depends only on zeta for the familiar reasons. So this capital gamma is also a constant. Right, so the first time you write that down, you think you made a mistake of the sign because you got negative surface tension, but then you immediately realize you haven't. It's something, again, I've alluded to already, that cell-cell division pushes cells against each other. So this rim has a contribution of compressive stress. So this sign is correct. This is a surface compression rather than a surface tension. So I think there's I think only one slide to go. So this is the final slide. So this then summarizes what the minimal model looks like in the Stokes flow case. We are doing, in collaboration, numerics on this. There's nothing to report yet, but this is the formulation. So in the core, the scalings for the stresses are recorded at the top. Again, we've got, this is now completely vanilla Stokes flow as far as the field equations are concerned, but with a single change. It's no longer div V is 0. There's now this net volumetric sink. I'm just going to finish off by saying what the difference from the standard case are. The free surface conditions are as recorded here, which are implicit in things I've already said, this net surface tension coefficient and this modified kinematic condition. So there's also been quite a lot of work on Stokes free boundary problems, and amazingly you can make an awful lot of progress with surface tension, even with surface tension in 2D by complex variable. So I suspect this may be amenable to some complex variable approaches as well, but I've finished just by recording what the differences are. So there is this volumetric sink. It's not standard incompressible, div V is 0. the kinematic condition has been modified too because there's a surface source. So in some sense, those two are in competition. And finally, there's this surface compression. So this is a bit viscous buckling instability if gamma naught is less than big gamma. And that was well known, actually. I think in the biological context, it was first found in cell-based models. So you'd have a ring of individual cells and do the mechanics between them and find they buckle. I think in some sense, this is the best way to abstract that mechanism into this type of formulation. So that viscous buckling is a further instability mechanism, very different from the ones I've alluded to in Darcy flow, which again drives instabilities. And in this regime, Stokes flow free boundary problems are almost always well posed. If in this regime where you've got negative surface tension, I think it's ill posed. So that then, and my final comment, there's the question of how you further regularize it. And the natural thing is to put in surface viscosity or surface elasticity. But one would want a good reason to do that. But anyway, I think there's interesting modeling questions and mathematical questions associated with this free boundary condition. So they're the things I wanted to say. Asymptotic derivation of minimal models and some steps towards their analysis, again by asymptotic methods. So thanks very much.
Okay, do we have any questions for John?
Have you looked at planar fronts?
Say again.
Have you looked at planar fronts?
Yeah, so in linear stability terms, yeah.
So linear stability, I mean, I'm wondering if it fingers.
Yes, it does.
And do you know, do the fingers go to a constant velocity?
Right, so the Darcy case, no, because the growth business makes it significantly more complicated in some respects than standard Saffman-Taylor. Stokes, with the final statement, is ill-posed, so it's not clear what the question would mean. But the short answer in both cases is no.
Yeah. I mean, so the interesting question for cancer in these models is if you look at this as a mechanism for growth and seeking out nutrients, you want to know, is it going to coarseness, going to put out long fingers, and what the selection mechanism is. And it sounds like you're just on the verge of that at this point.
Right, so to downplay this, the Dirichlet condition for concentration is of course the simplest, but once you start developing long fingers, whatever else, you're going to want low concentration at the tip of the finger because it's all in the outside. So the Mullins-Kirk or whatever you want to call it. So the nutrient concentration there is going to be low because it's been consumed on the sides. In other words, you want to solve the concentration outside as well. We've done the linear stability of that. We haven't done anything non-linear on it.
Okay, do we have any more questions for John? But let me ask a quick question. Is there any way from a modeling point of view that one would know that, the Darcy flow is maybe good enough? Do I need to do Stokes? How do you decide on non-mathematical grounds which one is the reasonable one to do?
Well, I would try and be a mathematical modeler and do it on physical grounds. So the way people try and sell Darcy for cancer growth is, one of the ways is because you treat the extracellular matrix as a porous material. I mean, I don't buy that because you're going to move the extracellular matrix when the thing grows. You're not just squeezing cells through it. So in that sense, I quite strongly think Stokes is the right minimal model. If you want to get serious about biological complexity, you have to go way beyond that anyway.
Okay. All right. Okay, I'm going to make one comment. That the D for the mean first passage time is actually outside, but even if it depends on X.
Yeah, I'd like to see why. Yeah. Yeah.
All right, okay. So let's thank John again. Thank you. And we'll reconvene at 3:30, is that right? And, okay. So our last speaker today is Chris Lustri, right? Who is going to talk to us about the asymptotics of some discrete systems. Okay.
Hi everyone, thanks for coming. It's nice of you to come back after the long break. I'm delighted. Today what I'm going to talk about is how we can apply conventional, classical, semi-classical type asymptotic methods that were developed in continuous settings to discrete problems. And what's interesting is some of the things that you would think would be hard aren't, but some of the things that you would think would be simple also aren't. So the idea here is that applying straightforward asymptotic techniques, things you learnt in, fourth year undergrad, you learnt your multiple scales, you learnt your matched asymptotic expansions, all of these ideas, applying them to discrete problems is typically possible, but it's not always simple. And part of the reason for that is when you have a discrete problem, you have to be very, very careful that you don't accidentally throw away behavior that occurs on a discrete scale. So one of the sort of most common ways people approximate functions on discrete settings is long wave approximations. They say, well, let's assume that nothing changes very quickly, that it's close enough to continuous that we can do that. Throw down a Taylor series expansion, treat it as continuous, and everybody is happy. And a lot of the time this works. This has been used to get important results in, say, the discrete nonlinear Schrödinger or other equations of that ilk. But sometimes you can lose features. Any feature that changes rapidly on the discrete scale, you often see things with a -1 to the n multiplier, something like that. You have to be very careful that you aren't actually throwing it away. Ideally, what you would like to do these problems is an asymptotic method that incorporates this information so you can still do your long wave approximations, but also sort of keeping an accounting of what the discrete scale variation is. So I'm going to talk about two problems, and in particular these are problems where I've taken a relatively well-known asymptotic technique and I've applied it to discrete problems in a way that preserves discrete elements of the solution where necessary. In the first problem, I'm going to look at what's called a slowly varying logistic map to look at how we can use the method of multiple scales and actually how we can resolve some open questions that had been bouncing around in the literature for a while. And in the second, I'm going to go back to a topic that is very close to my heart, exponential asymptotics, and I'm going to talk about how I was able to explain certain behavior you see in diatomic lattices, chains of particles, and we're going to use the total lattice as an example. Both of these methods are quote-unquote continuous. They are methods that essentially rely on being able to take infinitely small distances. Epsilon gets arbitrarily close, arbitrarily small. But we're going to do this in a way that doesn't lose the discreteness. Now, problem one, it seems like it shouldn't be difficult. The method seems very obvious, but it turns out it is. Problem two, it seems like it should be difficult. It seems very unlikely that you would be able to pull this information out in a straightforward fashion, but because of the structure with it's a bit of a blind, but because of the structure of the problem, what we're looking for is actually not so bad. So first, problem one. Problem one is the sweeping logistic map, and I think the logistic map is something we are all familiar with, but a little bit of a recap. If you have the logistic map, it's an iterative map, you have xn, you use the map to get xn plus 1, you have this parameter r. Now if r is less than 3, what you'll find is this converges to a single solution. You run it a lot and it eventually settles. If r is between 3 and about 3.5, I can't remember the exact number, then what happens is if you run it long enough, it settles on a period 2 solution, period 4 solution, and you get this period doubling. This is relatively well known, and I don't think I'm going to bring anything particularly new to the table on the logistic map. But what I'm interested in is what happens if we allow r to vary a little bit. Now this is not a critically important problem. It was sort of selected because it has the behavior we were looking for. This behavior was picked because it displays a certain kind of phenomena that I will dig out. But it's a pretty little problem, and I think you'll enjoy what you see. If r is sufficiently slow, if r changes very slowly, so I've made it epsilon squared makes the algebra nicer. We would expect this to reproduce the bifurcation diagram. If this is changing very slowly, at each point it essentially has time to settle. So you would think it would settle, 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 you'd cross through here, and now it has time to settle to the period 2 solution, and so on and so forth. But it turns out that if it was that, this would be a short and boring talk. It isn't that. What you see is this. So R very slowly, and it shoots straight through the bifurcation point, effectively, to all intents and purposes, not noticing it until quite some way has passed, at which point it all of a sudden realizes it's not where it's supposed to be and jumps up to the period 2 manifold. And it does the same trick down here as well, and at this point the scales start to get meshed together. I'm not going to dwell on what's going on here because, you know, it's all a bit, scale separation has disappeared. I'm actually going to focus on the first transition. So the question is, what are we seeing? Well, what we are seeing, oh, sorry, a piece of information. That gap, it turns out, is going to be 1 over epsilon log 1 over epsilon square root. It's an odd scaling, but a scaling which, if you've worked on a certain kind of problem, jumps out at you immediately. And that kind of problem is this. There are some French speakers in the room. I think you're probably already there. What we are seeing is a discrete canard. So if you play it backwards, it becomes more apparent what's going on. It overshoots, jumps up, then if we change the sign, it goes back and shoots back the other way. Now, canards are well studied. That scaling was very apparent to canard experts. Martin Weschelberger yelled out what the scaling was before I had a chance to even say it, which was a little sad. But it's actually unusual because what we're seeing is not a typical canard, it is a discrete canard. That is my best joke. That is as good as this gets. It's a discrete canard. So we want to say, can we use asymptotics to pick out the scalings at which this happens? Can we join it together? Can we follow the solution? And we can. So to capture this delayed bifurcation, we use multiple scales. Now, this, it turned out, was a surprisingly incendiary question. So I did this work with Cameron Hall, who is at Limerick, who is moving to Bristol. He brought this problem and we chatted about it, and what he told me is the literature actually can't agree on what the best place to do this kind of multiple scales approach is. Sort of historically, the obvious classical idea is you have a discrete fast time scale which captures just the n variation, and you have some slow time manifold on which it's modulated. But more recently, some very apparently convincing arguments were made that you can't do that. You will still throw stuff away, and what you need is a discrete slow scale and a discrete fast scale. Now this is a bit sad because discrete slow scale means you're winding up with partial difference equations everywhere, and it's just a complete mess. So that's not what we want. And so we went back, and the paper where this was sort of laid out was a 2008 paper by Van Horsen and Tabraka, who used this equation is kind of an example of why you can't do this. Now, to cut to the end, they're missing something here, which is fine. It's a detail that you can get around, so I'm not saying this is a big problem. But they define their continuous slow time variable t equals epsilon to the n. So it's slower by a factor of epsilon, and obtain this solution. Now this solution has finite time blow-up, and it is very clear from the equation that there is no finite time blow-up in this system. So they contend that something has gone wrong. They resolve it by using discrete multiple scales with a discrete long time scale, which is hard to solve, but they do it. But actually, what you want to do is a little bit simpler, because the real problem is not that this is intrinsically inaccessible to a continuous slow time scale. It's that the series loses its asymptoticity at t equals 1 over theta, plus this is strict order, so something times epsilon. And we can fix this not by throwing away the whole approach, but instead by introducing further time scales as and when they arise. So in this case, it turns out we require an extra slow time scale, and we can capture the behavior as necessary. And it turns out that's what we'll find with ours as well. So sorry, yes? No worries.
Yes.
Just to make things clear, so from the pictures you showed when you add this epsilon, right?
Yes.
This is asymptotic behavior, so that's what you should get in the limit n goes to infinity, right?
In the limit epsilon goes to 0, so...
So it's a double limit, right?
I'm not taking n goes to infinity.
But in that case, how do you know that on which, how do you obtain this curve?
This curve was obtained numerically. I just n equals 1, n equals 2, n equals 3.
And you repeat it?
Sure, and because epsilon is small, n does get quite a large value, but they're linked. It's not a double limit. The size of... so epsilon is the small parameter. This is more of a scaling thing. So to get epsilon squared n equals order 1, n does have to take large values, but that is captured in the continuous time scale. So
maybe just if I can ask it differently, does this curve depend on the epsilon? Would it be shifted if you change the epsilon?
Yes, particularly this gap changes length. Okay. That's all that happens there.
Thanks.
Okay, so we're going to take our sweeping logistic map. I'm going to start it at 3. So, you know, we're not going to start before. So we're starting at the bifurcation parameter and we're letting it play. And sure enough, it goes from the period 1 solution, and at about 3.08, 3.1, it realizes it's meant to be on the period 2 manifold and makes its jump. So what we're going to say is what happens if we write this in terms of a multiple scales parameter. But before we do that, we're going to do some setup. We define our R to be the sweeping parameter for simplicity, and we compute the period 1 and period 2 manifolds. Period 2 is actually not important to the analysis. I just put it up there because I calculated it. The period 1 manifold is the important thing, because we are actually going to rescale the sweeping equation so that we are sitting on the period 1 manifold. So in some sense, as n goes to minus infinity or minus whatever, capital X goes to 0 because that is on the manifold. So what we want to see is this capital X grow in some way as we cross the manifold. So we introduced our slow time scale. So now we have our fast time scale n and our slow time scale t, and what we're hoping is that we can capture this behavior. It turns out our initial condition we have to adjust a bit as well. This is all basically just calculation. You can go through it. I could go through it with you if you'd like, but you can trust me.
So, forgive me for this, but should the left-hand side have a minus sign between xn plus 1 and xn and t? You gotta turn it on.
Sorry?
Should the left-hand... Can you hear me now?
Yes.
Should the left-hand side be xn plus 1 minus xn of t?
No. That is very definitely right. I don't know, we could churn through the algebra, I suppose.
I trust you.
You can trust me. If that was wrong, then almost everything from here on would be. But that is, we read these calculations went through.
Help me out just a little bit more then. If epsilon 0.
Yes.
Oh, no. So the eigenvalue is -1. It's a flip. Okay. Yes, I agree. Thank you.
I'm glad we were able to come to an agreement. So what we do is, you know, we expand it as a Taylor series in much the normal way, a Taylor series in epsilon. And we just pick out the first 2 orders, as we would do with any multiple scales problem. The first order gives us the general form of x naught, and it tells us that we have this -1 to the n periodicity. If we tried to do a long wave approximation, we would have thrown that away, because that can't be captured on any scale slower than n. We also have this arbitrary function, which of course comes from the secularity condition at the next order. So with a little bit of work and going back to our initial condition, we find that we can get x naught. We turn the handle a bit more. We get a few more correction terms, but basically it's the same process. It's multiple scales. As long as you can solve linear difference equations, that first equation won't give you too much trouble. So we do this in other order and we get this. This is just equations. Let's look at a picture. And it follows it pretty well. It captures what's going on until it comes time to find the period 2 manifold. And then it has no idea what's going on. Completely loses it. At this point, if we were inclined towards throwing away this whole method, we would say, look, it's failed again. You can't use a continuous slow manifold, but you can. You can, because all that's happening is our equations are rebalancing. There is a term that is joining the dominant balance that we hadn't previously been considering. So we need to introduce a late time variable. We need to work out what that gap is, and we need to find it. So to do that, this is a bit fiddly, and I'm happy to go through it with you if you want, but basically we look at the series in such a way that we can pretend ignore the -1 to the n variation by considering the two-step term, every second term. And then we can find that the critical time scale is this k. And k is the solution to a transcendental equation, but it does have this asymptotic behavior, log of 1 over epsilon. So we have this, and this is our outer scale. The particular scalings aren't important other than to notice that it's a bit unpleasant, but also it's the same scalings you see in a continuous canard. So it suggests that we're on the right track. Here we've just rewritten our system in the original coordinates. It looks a bit funny, but of course t equals epsilon n, and we've put another epsilon in there. M is a discrete parameter with this gamma just to indicate that we're in a different set of variables, and we've chosen this gamma between 0 and 2 so that n and m have the same odd even properties. Just not important to what you'll see here, but what is the gamma is a very reasonable question. So our new variable is this xi. And our new governing equation is this, and we expand as a series, and even though I have epsilons and k's, because this problem is nice, I don't have to do a double series. If the problem wasn't nice, you would have to do a double series, but we just basically say, look, we can just treat k as order 1 for all intents and purposes, because it's a log of an epsilon. We did it the hard way first, but this is better. So we solve that, and we get this slightly more complicated expression. F is Dawson's integral, which is related to the exponential integral. Is that sensible? I think we should look at some pictures. You can match back to get this arbitrary Kp, which is 324, a number that doesn't come up a lot, but was quite pleasing here. We put it back all in terms of the original variables. So now we're saying, let's collapse everything back onto one scale. Let's see if it works. Black is the exact solution, dashed is the one-term approximation. So this is about size epsilon, it's the right error. You can calculate more, you can get this error better, but the critical thing is we were able to capture the jump. We were able to capture the jump, we were able to find the other manifold. You'll notice I didn't program the other manifold into this at any point. It found the period 2 manifold on its own. So that's good, and what this basically says, I mean, the problem itself is not important. It's kind of cool to see this discrete canard behavior, but really what we wanted to say is you can, if you're careful, still look at fast, discrete, slow, continuous scales, but all of a sudden there's a lot more terms that you need to be very careful about losing the asymptoticity. In this problem, the asymptotic term that bubbles up and breaks everything comes from the third correction. So you often have to dig in a little bit and make sure that you're not missing something important. Naively applying multiple scales would suggest this can't work. But if we don't throw the whole approach away, if we're just very careful about how we apply our asymptotics, then we can retrieve the answers and we can see what we're looking for, which is this approximation. So this was sort of the warm-up problem. This is a bit of a taster. The real problem. Oh, please, yeah.
Can I ask a question here?
Yeah, please.
So I've done problems with Justin about delayed bifurcation in PDEs.
Yep.
Whereby it's the same thing like in ODEs, where it's the integral of the static eigenvalue from over the pass sweep. So you linearize. You want to find out, can you predict when the takeoff point is? Right? So that for this continuous system, it's always the integral of the eigenvalue must be equal to 0, and the sweep. So is there some recipe like this for your discrete problem? If I give you an arbitrary discrete problem with a flip bifurcation.
So we didn't attempt to dig a recipe out, but it wouldn't surprise me, although you would have to check to see how it holds up with the discrete nature of the problem. Yeah. Because all of a sudden you're approximating integrals by sums and so on. So I haven't tried it. I can't possibly say for sure, but it has the right scalings as other problems of this ilk, which suggests that any highly generic methods should still apply. But you may have to be a bit careful, which is why I'm not willing to confirm, but I might sit down and check. I don't know the answer off the top of my head.
Okay.
So that was problem one. It's oh, Justin, yeah, go for it.
Sorry, Chris. So you said that you started at 3, is that right?
Yes.
So what if you start farther back, does it...
That is a deeply insightful question. So I did cheat a little bit. Does anyone know why I cheat? How I cheated a little bit? Did anyone spot it?
Okay, because it's going to be, the delay should depend on how far back you were initially.
Indeed, and the reason for that is I started an algebraic distance from the manifold, and that makes the calculations a lot easier. If you start further back, you get exponentially close to the manifold, and that delay pushes the delay back further. Exactly right. And this is incidentally the reason I glossed over the fact that I wasn't doing the double one, because of course that's exactly the situation we're in. It's now exponentially close, which means if you apply this analysis naively, it doesn't go as far. You can still do that analysis. We've done calculations to satisfy ourselves that that was possible. But for some certain technical, we didn't do it for the paper because when you're that exponentially close, all of a sudden basic numerical methods stop working, because even your numerical fluctuations mean that your asymptotic predictions just don't work. Because what's actually causing this jump off is not moving away from the exponential point, it is literally numerical error is what actually causes the jump off past that.
Or unless if you compute in 32 digits of accuracy, then maybe you can yeah, we've had the same issues with the delayed PDE. Yeah.
Yes, so that is exactly why we buried the lead a little bit and started just an epsilon away from the manifold. The maths does work out, but you just can't see it on a computer without being very, very careful. So, are there any more questions about the first part before I move on? Because, good. So problem 2 came about from, I think, Siam nonlinear waves in about 2015. I bumped into Mason Porter, and Mason showed me some pictures and asked me, you know, was I able to sort of explain what was going on here? It looked like something I might know a little bit about, and it did. It took me a few years to pin it down, but we did get there. But to start off, we're going to take a step back and we're going to talk about exponential asymptotics. Some people in this room know exponential asymptotics very well. You can doze out, check the cricket scores, whatever it is you want to do. This is going right back to the very beginning, which is something we learn when we learn about order, which is that any exponential is smaller than an algebraic term. E to the minus epsilon, 1 over epsilon, is smaller than any algebraic power of epsilon in the limit that epsilon goes to 0. And typically that's not a problem, because if you're only e to the minus 1 on epsilon big, chances are you don't matter very much, except when you do. The kind of situations where you really want to know what's going on this kind of scales, I broadly break them into 3 categories. The first is when maybe you've got something that's exponentially small in the bit of the domain you're looking at, but if you move to another part of the domain, all of a sudden it matters, and you threw it away because you thought it was exponentially small. Typically this comes up in the asymptotics of special functions, which I'm going to use as a pedagogical example. Sometimes you see qualitatively distinct behavior on this scale that doesn't appear anywhere else. In my PhD thesis, I studied water waves, and a big part of the whole water waves idea is these waves, that your free surfaces were waveless at any algebraic order of epsilon, but there were still waves there. They were just exponentially small. And finally, and I won't really talk about this today, but this is quite an enjoyable application, is selection mechanisms, things like Healy-Shaw finger widths, where you have this exponentially small quantity that actually determines the behavior of the solution at macroscopic visible orders. And that's quite important, because then you have this e to the minus 1 on epsilon affecting what's going on in the solution, even at scales you can see. So in each of these cases, you try and apply an asymptotic approximation power series, and it just can't see it. It can't see to the e to the minus 1 on epsilon. As an example, I'm going to show a function I think we're all familiar with, the complementary error function, just to show you what happens when you do look at these orders. This is not my research. This is, in fact, I didn't even do this example first. This example comes out of a paper that I think John was an author on, so good job. So what happens here is the complementary error function with large argument has different asymptotic representations depending on where you are in the complex plane. If you're in this blue region, it has this series representation, and that each term in this series is exponentially small, so obviously this is an exponentially small quantity, which matches up to what we expect to see. But if you cruise around into this green region, you have the same series, but all the quantities are now exponentially large. So now, instead of the tiny solution there, it's huge, it's gigantic. And then you shoot out into this red region, and the asymptotic representation is 2, and plus some exponentially small stuff. But the 2 has come from somewhere, and it's not immediately obvious where that happened. And this is kind of akin to what Stokes noticed. He noticed it with the Airy function, which is the other sort of classical example people use to illustrate this, is there is some behavior that's appearing somewhere. It's switched on somewhere, but we couldn't see it because the thing we're looking for is exponentially small compared to the series. Fortunately, this is such a simple problem that we could just, go back to undergrad and use the method of steepest descents. If we're in this first quadrant, so we start here, and I'm starting close to the vertical axis, but anywhere in this quadrant, the steepest descent curve just shoots us straight out to infinity where we need to be. And we can use our method of steepest descents, and we can put together the series, and it's exactly what we were told. But the minute we cross that axis, the steepest descent curve doesn't take us where we want to go anymore. It takes us out to minus infinity, which is the opposite of where we want to go. So we have to add a second contour, which takes us from minus infinity to infinity, and sure enough, that integral is just 2. So in fact, our series, this still produces the same series term, but this second contour gives us this 2. So now we've picked up this term, and remember, these are exponentially large at this point. So we've got this exponentially large stuff, but we've picked up an order 1 term. We couldn't see that with a power series because it's exponentially smaller than anything else. So actually, the full picture looks like this. You've got the first quadrant where it's this series plus 0, and you've got the second quadrant where it's this series plus 2. So something quite important happened as we crossed the vertical axis. We crossed what's called a Stokes line, where something switches very quickly. Of course, we know that the complementary error function is continuous, it's analytic, it's entire. It seems odd that we would have this very discontinuous change. So maybe we want to take a slightly closer look at that. So say I didn't have the integral representation and I just wanted to be able to pick out what's going on across that Stokes line. Then I would use exponential asymptotics, asymptotics beyond all orders, hyperasymptotics. It has a few names. But basically, no matter what you call it, it generally boils down to 2 steps. The first step is you optimally truncate your asymptotic power series. That's such an easy thing to say. You find every term in the power series and you cut it at the smallest one. Because it turns out that when you do that, your remainder is exponentially small. This was proved by Michael Berry in the mid-90s. And then the hyperasymptotic step is essentially rescaling the problem to look directly at the remainder. So by essentially taking all the algebraic part and throwing it away, we were able to look solely at the exponentially small remainder. We're linearizing around the optimally truncated series. This is possible because asymptotic series of singularly perturbed functions normally diverge, which means there is a smallest term we can cut it at. So basically, to optimally truncate, we just go, well, that's small, that one's bigger, that one's bigger, that one's bigger, let's cut it off there. Truncating the series gives us our remainder term. So now, rather than our series to infinity, we are now saying it is equal to a series up to the truncation point added to a remainder. And the remainder is now what we're interested in. So it turns out finding the optimal truncation point, it's a bit of a pain, but if you know all the terms, you can find the smallest one, the smallest epsilon to the 2nwn, and just cut it off there. And this typically occurs after a large number of terms. That's very common. So in fact, this truncation point n has its own epsilon dependence. It's 1 on root epsilon here, but often 1 on epsilon. And the correct n forces the remainder to be exponentially small. So Now, once we've done that, we can throw it back into the series and, as I said, rescale the problem to get an equation for Rn. And then we can use matched asymptotic expansions to work out what Rn is doing near the Stokes line, math, and you find out that Rn is 1 plus this error term, which essentially rapidly changes that Rn from 0 to 2 as the Stokes line is crossed. It's not discontinuous. It is in fact varying smoothly and rapidly in the neighborhood of the Stokes line. So what we actually have is not our discontinuous blue and red region, but this blue region, and then a region of width about 1 on root epsilon, this purple region, where it varies smoothly as an error function, before being spat out in this region. So now we have this expansion here, and it is valid, it is a uniform expansion, valid beyond all orders throughout the entire upper half plane. So by using this optimal truncation method, we were able to pull out information that was buried beyond all orders of the asymptotic series, smaller than any term. So solving for these beyond all order terms, we were able to do this because I could optimally truncate. And I was able to optimally truncate because I could go back to here, look at every single term, and work out which one was smallest. Which is fine if you can work out every single term, which for any problem worth its salt is not possible. So we need to adapt. You can't find every term for most problems, but if we look at the analysis here, I didn't need every term. I just needed Wn. I just needed the biggest term we kept. But that seems like a bit of a blind, because actually to get Wn I needed Wn minus 1, to get Wn minus 1 I needed Wn minus 2, and so on and so forth. It's a house of cards. Except it turns out that asymptotic series are more predictable than we give them credit for. Even if we can't work out W2 or W3, it turns out working out what we call the late order terms, Wn as n goes to infinity, is a little more doable, because typically, given some certain criteria, divergent series often diverge in basically the same way. What's happening is you've got some leading order solution with singularities. You repeatedly differentiate them. At every order, the singularity gets stronger. I differentiate it again, it gets stronger again. I differentiate it again, it gets stronger again, until eventually our repeatedly differentiated singularities are just blasting all the nonlinearity out of the water. So you may not have a clue what's going on in W3, but you kind of know what's going on in W infinity. As long as you know where the singularities in the leading order behavior are, then you know what the late order terms will do, with some extra, bits and bobs around. Even if you don't know everything that's going on in between. And the trick here is this quantity here, this chi called the singulant, which encodes the information about the singularities. The singulant is 0 at singular points of the leading order, or early orders if you want to be pedantic. So the singulant and as you can see, as n gets larger, the strength of the singularity gets stronger, and stronger and stronger and stronger, and Dingle showed that in fact, you can rigorously show for classes of equation that the late order asymptotic terms will be completely dominated by a sum of these terms associated with each individual singularity. So if you know where the singularities are and you know how it diverges, then you can basically write down the remainder. I mean, we can show this, but it always looks the same. Takes this prefactor at the front, and then you've got e2 minus the singulant over epsilon, or square root of epsilon, or epsilon squared, or whatever your scaling is. So the size of this is exponentially controlled by the singulant. The singulant is the money. That tells us what we need to know. And in fact, you can show that it tells us where the Stokes lines are, because this simple condition is satisfied by every Stokes line. And some things that aren't Stokes lines sometimes. You have to be a bit careful. But as long as the real part of the singulant is greater than 0 and the imaginary part of the singulant is 0, you have a Stokes line candidate. And for the sake of this talk, a Stokes line. So knowing the singulant tells us everything we need to know about the Stokes structure. It's the quantity that tells you what's going on. So we can also get the W and the gamma and all of these things, but in terms of what's going on, we're gonna draw our focus to the singulant for the sake of this problem. So to summarize that, because that was a lot of information very quickly, you write the asymptotic series equations and then you prescribe an ansatz for the late order terms. So you may not know W2 or W3, but if you've got singularities in W0, you can work out what Wn is going to look like as n goes large. We truncate the series optimally, and now remember, we know that the truncation happens after a large number of terms. I stressed that. So near the truncation point, Wn does look like this, because n is large. So we truncate the series optimally because we basically know what the series terms look like at the bits we're interested in. We figure out the remainder form and we compute the remainder in the neighborhood of the Stokes lines. And that's matched asymptotic expansions, but we're not going to dwell too much on that today. It's a fairly straightforward calculation. Once you've got Rn, you mostly know what's going on. Once you know where the Stokes lines are. So, why do I care? That is a huge amount of work to find something that is very, very small. So, I want to talk about the problem which motivated this work today, which is what happens when we have chains of particles that can only see their neighbors. You can loosen that, but we won't today. So each particle can only see its friend to the right and its friend to the left. Particles with constant mass, relatively well understood in as much as these things can be. What we're going to look at is what happens when you have alternating mass. So this is the first step to understanding the effect of heterogeneity on these kinds of problems. So the experiments were done with periodic masses, but a similar analysis goes to, say, a single point defect, or say a double well type thing where you've got two defects that can see each other, something like that. And typically equations of the form we're going to look at look a bit like this. So you've got your Yn, which is your heavy particles, and you've got your Zn, which is your light particles, and the mass ratio is epsilon, so the mass ratio is very small. And you've got some potential V, and your potential V basically says how do they interact? What do they do when their body moves? So we have this system of equations. Now the particular experimental results that I was shown were a chain of beads that had Hertzian interactions, which means they blindly bumped into each other. And they sent some solitary waves down, or what looked like solitary wave solutions, except they left behind these little trails. Were they exponentially small? Probably. We've seen other things like that before. So the question is, could we calculate what these tails were? They don't appear in the algebraic series, suggests they're probably exponentially small. So here is an experimental paper which shows some of this stuff. So this is a different kind of nearest neighbor system called a woodpile system. This is something that we're still trying to get the maths right to explain, but you can see that there's these little oscillations, and you might be tempted to say it's an experiment. Of course there's stuff hanging around behind, but actually they're very predictable. This paper goes a long way to showing us that they are a real thing, not just kind of the air conditioner malfunctioning. And here's some numerics to sort of see equivalently what's going on. You can see that we have these oscillations. I have stretched out the axis spectacularly to be able to see this. But you see these oscillations in the wake of the wave that's traveling from left to right. So these are the sort of behavior we would like to see, except those waves are exponentially small, so how can we dig them out? Now, similar problems have been done in continuous systems quite a lot. The gravity capillary problem is quite a famous one, and possibly one of the first ones where John Boyd, Roger Grimshaw, these guys pulled out this kind of behavior. But up to this point, no one had done a discrete problem. So what you see, here's an example. So this is the total lattice. We picked the total lattice because it's integrable, which means it has a nice leading order, which means at least one thing in this problem was straightforward. And here's the diatomic one. So essentially the same problem, except now you've got these light red particles, which according to this equation just basically oscillate indefinitely. Obviously not indefinitely in real life, but that's other physics coming into the problem, whereas the total lattice is already a pretty idealized situation. It doesn't conserve energy. But the question is, can we predict the amplitude? And the particular question we wanted is, can can we send down pulses which don't leave those oscillations? Can we find proper classical solitary waves? It's one thing to say the amplitude is this big. It's another thing to say the amplitude is this big and sometimes there aren't any waves, because that leaves the smallest amount of deformation of the lattice, the least energy loss, which means your model is gooder for longer. So, being as I was in an integrable systems group at the time, it made sense to do the total lattice, which is integrable. And so I have this, and I decided, set a traveling wave variable. Fingers crossed, everything travels with the traveling wave. It did, and that was nice. Expand as a Taylor series. So, the Taylor series is now Y0 and Z0 are your leading order terms. Y1 and Z1 are your first corrections, and so on and so forth. So we get this Taylor series expansion. And we can get the leading order solution because the leading order solution to the total lattice is easy-ish. Exponentials of Sainz's. Critically, Z0 is just the average of its neighbors. It's very light, so to leading order, it doesn't really move on its own. Just kind of gets dragged around by the heavy particles. And these are the points where the leading order is singular. You'll notice these are complex. To do this method, you are always analytically continuing. So these are solutions in the these are singularities in the analytic continuation of Z0. There are also singularities in the analytic continuation of Y0, but for reasons that will be apparent later, we're mostly going to focus on Z. Y just comes along for the ride. So we have these singularities. You can pick the signs independently, so there are 4 of them. There are 4 singularities in the analytic continuation, which means there are 4 exponentially small contributions that we need to pick out. And because we have a series expansion, we can just match orders of epsilon and get a recursion relation for yj in terms of previous y and z terms, and zj in terms of previous z terms. It doesn't look super nice. So we've got Z0. We'll hold on to that. But now we need to do our ansatz. The oscillations are exponentially small. Obviously, as I discussed, we can't just go, well, what's in Y1? What's in Y2? What's in Z3? What's in Z4? We will never find those oscillations. Instead, we need to use exponential asymptotics, and recall the first step was to make our ansatz. What do Yj and Zj do as j becomes large, or r as I decided to call them on this slide? So let's take our recursion relation. It looks gross. It's very hard to imagine how I'm going to be able to pull any useful information out of that, but it turns out that at late order terms, not every one of those things matters. Only the blue terms matter when j gets large. So you've got your yj, you've got your zj, but actually we can throw away that term and that term and that term and that term. So when we put our ansatz equation back into this system, a lot of the difficulty kind of washes away. And this is why the discrete problem is not such an issue. Here, we have a gross forward-backwards difference equation. We're going to have to be very clever about it. And that is true for algebraic orders. But as j goes large, the system decouples. And in fact, this is why I only really cared about z, because at late orders, even though I've got this discrete, disgusting, interrelated system, zj does its own thing. And furthermore, it just drags y along for the ride. So as long as I know what zj is doing, then I know everything I need to know. The second equation is completely decoupled. So now for the sake of this talk, I'm just going to throw away y. Y is there. In the paper we calculate it just to show we can, but really z is the money. And now that we have this much, much simpler equation for z, because the discrete stuff is decoupled, I can apply my late order ansatz with no problems. Recall that chi was equal to 0 at singularities in the leading order, of which there were 4. Means that I can just throw this ansatz back into here, do an asymptotic matching as j goes large, and I can get an equation for the singulant. It's a differential equation, first order, and I have one condition, chi equals 0 at some singularity. So I can solve that, and I can get z and I can get gamma. Gamma is easy, z is hard, but neither are important for this problem. Neither are important for this talk. So this singulant equation is basically what you're looking for when you set out to do this problem. Because remember, once I know the singulant, I know where the Stokes lines are, I know how big things are, I have up to exponential order controlled the amplitude. So this tells me what I want to know. And what it tells me is this. So I'm going to talk you through this. What we have here is the full Stokes graph. Dashed lines are Stokes lines, which is what we saw before, where something switches on and switches off. Jagged lines are branch cuts. Solid lines are anti-Stokes lines, where small things become big. But remember, we're interested in the physical behavior. So we're really only interested in what happens when the wave variable is real. What's going on here helped me figure out what was colored where, but in terms of what we're seeing, we really want to know what happens as we go along this line. So our leading order singularities were here, 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 and here. And each one causes a different quantity to be switched on. So I get late order contributions from my Xi2 singularities as I cross this Stokes line. So I get these two contributions. It turns out they're complex conjugates of each other, so I get real oscillations switching on here. Then I keep going and I hit the second Stokes line and I switch on another set of oscillations from these two singularities. Again, complex conjugate pairs. So now I have two sets of oscillations that have switched on. So the wave is going this way. Ahead of the wave, obviously undisturbed. Essentially the front of the wave kicks off one set of oscillations and the back of the wave kicks off another set of oscillations. So if I just look at the exponentially small terms, I have something that looks like that. Now, we weren't actually, full disclosure, the first people to consider a diatomic total lattice. Anna Weinstein and Doug Wright and some other authors had considered used a multiple scales method to get the full solution for, exploited the integrability to get a full solution for everything beyond the leading order. And that meant that they could basically plot everything but the leading order, but what we were able to do was to specifically extract the oscillations. And this actually helped us to say a little more about the system that had previously been said. So, wave is going right to left, nothing, nothing, nothing. Wave front hits it, wave back hits it, and you get these oscillations. So we can now approximate the whole series. It's some optimally truncated sum of powers of epsilon plus this remainder thing, where S1 goes from 0 to 1 rapidly as we cross the first Stokes line, and S2 goes from 0 to 1 rapidly as we cross the second Stokes line. So these Stokes multipliers effectively encode that Stokes structure. And we can look at what the waves do in the far field. So the hypergeometric solution that they got in this previous paper is the red, and our asymptotics is the blue. And actually we had to evaluate certain integrals in the correction numerically as well. It didn't really cause a problem, but it's worth noting. So for various values of the wave speed, it's a pretty good match. And the smaller you get, the better a match it is, incidentally, which is important. Also important are these spiky bits. So obviously, what's happening here is that the amplitude is going to 0. So these are what we were looking for, because these are the special values where you have classical solitary wave solutions, because there are no exponentially small tails. If we could somehow pull those out, then we'd be looking pretty good. Previous attempts had not been able to pull that out. This was something quite new. But can we do it? Well, what's happening is that, remember, there's two oscillatory contributions, and it turns out they have the same amplitude. So if you turn them on in such a way that they are precisely out of phase, then they cancel each other out, and you get a classical solitary wave. But chi is this horrible function. I didn't even show it. You can evaluate it, but it's not really worth doing. But what we need is for this thing to be 0. We need precise cancellation. And it doesn't seem like that is possible until you think about how you get the singulant. So the singulant is the integral of chi dashed from the singularity to the point you're interested in. So in this case, this is the singulant for Xi2. But if I deform it to go through Xi1, then I can actually write one singulant in terms of the other. So chi2 is equal to whatever this integral is, plus chi1. And it turns out, and it's not easy to show, this integral is 2 pi I, which is nice. It's probably easy to show. I did it the hard way. There's probably a clever, easy way to figure that out. So it turns out that our oscillatory term cancels very nicely. because we need this to cancel, but we can write chi1 in terms of chi2, and it turns out that that simplifies to give us this condition, which is to say the mass ratio is 1 over an integer squared. That's a very simple condition, seems nonsensically simple, but actually what we hope to see is something like this. We've got our second condition switching on and causing the waves to cancel out. And they computed some values in this paper, and these were numerically obtained. And if you look at 1 over an integer squared, what you see is it's a very good agreement. So it turns out, by looking only at these oscillations, we were able to predict classical solitary wave solutions that you couldn't pick out using other asymptotic methods. Bit of a blind here, because of course it turned out I could apply this quite complicated method in a very straightforward fashion to our discrete chain. This is not always the case. There is a reason we started with this problem. So we're looking at some other problems where they don't decouple so nicely, and you can still deal with it, but it's a lot more of a pain. At this point we have to start gluing everything together. Because if I have problems that don't decouple, I need to put in my multiple scales, I've got my matched asymptotic expansions, I've got exponential asymptotics. It all sort of rolls together, but it still has Stokes phenomenon. These methods should still pull it out satisfactorily. So that is all I had to say about that problem. The problems that we're still looking at, I put up some experimental pictures before. I put up the Hertzian lattice, for example. Mason came to visit me a couple of weeks ago, and we made a lot of headway in doing that. That's quite complicated because the potential is asymmetric and non-smooth, so there's some other complications there. I've been looking at what happens with discrete KdV equations, because there are sort of straightforward discretizations, but there are also integrable discretizations. And integrable discretizations should retain the classical solitary wave behavior that non-integrable ones don't, like half done. Discrete nonlinear Schrodinger equations, which I've been doing with Dmitry Pelinovsky, looking at how bifurcation points and solitary wave solutions are affected by the discretization process itself. And something that I've done a lot of in the past is what is the Stokes structure of discrete Panlevet equations, discrete nonlinear special functions. These problems all basically use the same ideas I talked about, but this one here is the gold problem. Vortex dynamics in 2D nonlinear Schrodinger equations. So rather than a chain, we're looking at a lattice. We've got time as well. So Panos Kevrakidis and Hadi Sasanto have computed these types of solutions, but understanding their dynamics, we may need to bring these ideas to it. So when you look at Stokes phenomena in partial differential equations, you see this array of Stokes structures that we didn't really talk about here, and I'm hoping that they'll be reproduced in these lattice equations. So there's a lot more going on in this. It's a much harder problem, but it's something I'd like to do. I obviously need to acknowledge the other people who've worked on this. Problem 1 was with Cameron Hall, problem 2 was with Mason Porter. These other discrete problems, Nalini Joshi, my postdoc advisor, Stephen Liu, my PhD student, former PhD student, now doctor, and Dmitry Pelinovsky, who was over at Sydney on sabbatical when we got talking. That is all I have to say. Thank you very much for your time.
Okay, do we have any questions for Chris?
So does the integrable structure give you any shortcuts to figuring out, for example, exact solutions that don't have any oscillations?
So far it's been almost the exact opposite. It has broken everything. We are hoping that the integrable structure will give us this. And I was talking with Chris Howes about how this might happen, and we're going back to some other integral equations, but continuous ones, just to try and get a handle on maybe we can exploit the infinite hierarchy of symmetries. So we're thinking about Benjamin Ono and singly perturbed KdV, and just the problems themselves are sort of well understood, but we want to understand how maybe we can exploit the structure. But to be honest, the integrable discrete KdV is a complete mess that almost made me cry. for some reason, it absolutely destroys stuff, and it would be very interesting to know why. So yes, it does change things. At this point, it makes them worse, not better, which is quite a surprise. I mean, if I had to theorize, part of the thing is discretization, in some sense, kind of wants to make these oscillations. Often when you look at a discretized continuous function, discrete nonlinear Schrodinger, discrete KdV, all of these things, you find that there are waves that were sort of intrinsic to the problem and waves that were caused by the discretization, and you're kind of picking between the two. In some sense, an integral problem that can't really have either, but it wants to so badly. And it's a challenge to work out how that works.
I'll get a second one. And now for something completely different. So if you look at the bifurcation you looked at in the first problem,
yes,
it's a flip bifurcation.
Yes.
If you think about sort of generic bifurcations in discrete maps, there's three obvious ones. There's the transcritical, there's the flip, and there's the saddle node.
Yes.
Okay. Do you see the same phenomena basically every time if you look at slow variation of the control parameter in each of these systems?
I haven't played around with this transcritical. I have played around with the saddle node. You do see it. You have to be, again, very careful because the discreteness does come up and changes things. But the same bifurcation structures are certainly present, and they have the same scales, but you tend to need... So you're generally running the fast discrete scale, the slow continuous scale, and the very slow other continuous scale. So instead of tackling these as two scale problems as you would in continuous land, you're always juggling three different scales at least, which means that it's fiddly, but the same things are there. I have toyed around with the idea of thinking of this stuff in terms of geometric singular perturbation theory, which is kind of the most sort of, certainly the most possibly the most rigorous kind of taking a sledgehammer to it way of looking at these, but is well suited to these kinds of bifurcations. I haven't made full progress there yet, but I've been talking with some people about it. But they all seem to be there. The real question is it possible to introduce new ones because of interactions with this third scale? That's why I didn't dwell too much on the continuous interaction ones we knew, but rather sort of seeing if we can induce different kinds of bifurcations by this three-scale interaction. Fingers crossed, maybe, hopefully it'd be cool.
Do I get a third? Nope. You have one.
You have one more?
Well, I was just going to ask, if you go back and look at the first problem,
yep.
I want to check my intuition, and that is if you look at where it initially departs from the solution branch, can you get that entirely inside the linear theory?
You can get the departure inside the linear theory, but you can't reattach.
Of course.
Yeah.
Okay.
Yes, you absolutely can.
Yeah.
Oh, so let me follow up exactly with what Andy said. Because in the continuous systems, what Thomas Ernaud did for ODEs and different bifurcations, it's the integral of the eigenvalue. So you linearize, and then you track the eigenvalue as a function of the slope parameter.
Yep.
And it's when that balance condition holds where the integral of the eigenvalue is equal to 0.
Yep.
So you can live into the unstable regime is the takeoff point.
Yep.
So here in this discrete setting, if you linearize, right, you get a criteria that comes out like that as well for the different types, the three generic types of bifurcations. Is there some condition you can write down? Oh, there's a balance condition. Is there the eigenvalue of the discrete map that crosses through the -1 or something?
So we didn't investigate that specifically because we were sort of trying to make the multiple scales work, but you can see if you actually track all the terms, you can see which terms are starting to balance out. And I assume taking the sum of those, which is obviously sort of the variation away from the manifold, that will give you, I assume that will agree with the same condition. I haven't tried that, but it does seem like that would be how it would work. Because if you, so I didn't put it on there because it's just a whole lot of terms, but you can see which terms are bubbling up and causing you problems. And it's the same terms you would expect it to. after you've accounted for the discrete ones.
Yeah.
So the real trick is not that the continuous things are doing something wildly improbable, but that you have to actually go out of your way to account for the discrete stuff. If you don't, you actually get the wrong criteria, which sort of suggests that the discrete one does adjust that integral somewhat.
Okay.
Presumably because of the oscillatory nature causing some fast cancellation.
All right. Okay. I think we'll talk. Do we have any more? Okay. If not, let's thank Chris again.
Thank you very much.